situation. This is a global, definitely a global phenomenon that we have to deal with.
We're going to need booster shots at some point.
It'll be an annual shot then, probably too, just like a flu shot for quite some time to come. Yep.
Yep, for sure, for sure. Scott, I wanted to test something out here. Can I?
You want to test something? Sure.
Yeah. You'll see I have two instances. I have one that I'm using my audio and video.
You want to share,
and then I have another.
Or?
Yeah, I just want to share my screen on my other instance.
All right, go ahead and test.
So if I just test, so let's see here. Let me share my screen. Okay. So now when I speak, does it go away or does it stay on the video?
There's no video.
Can you see my screen?
I see your screen. It says astronomy video cameras.
Oh. Hello?
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 Oh, interesting.
Oh, you think the audio is taking over your
okay.
voice.
Can you hear me now?
Yep.
Yes.
Okay, so you couldn't hear me there. You couldn't hear me earlier, right?
No,
we could hear you, couldn't you?
Well, a little bit.
Okay.
It's like you said hello.
A little bit, yeah. So
stopped.
yeah, so that somehow they interrupted. That was interesting. So it uses the same stream. I have two different accounts. Okay, I'll figure out a different way of doing this. So what I'll do is let me stop sharing, or I'll just disconnect from here. What do you think there? Okay. I'm still here. Okay, you can still hear me, right?
Yep.
Oh. Okay, can you hear me now?
Yes.
Okay, good. Yeah, that's that. Having two sessions isn't good for my bandwidth, so I will not do that. Sorry. Thanks for letting me test that.
Okay.
Okay, now let me try something else.
Everybody's angry at me
Why?
because they didn't like the Einstein joke I told.
Well, it wasn't like you said that Einstein's not a planet anymore or something like that.
You must have told that before I came on. You can make everybody mad again.
Einstein's not a planet anymore, so there, okay?
There.
Neil Tyson told me so.
Neil Tyson told me.
And Mike Brown.
That's right. And Mike Brown. Actually, it was colliding phone calls. They said it at the same time.
Don't tell Alan Stern, though.
Or Chris E.P.
No.
Or 1,000 other planetary scientists.
Yeah. Or the Tombaugh family.
Yeah, right. Those guys. Or astronomers at Lowell.
Right.
But wasn't there like some sort of other revision that the American Astronomical or the International Astronomical Union was going to make that would affect Pluto's status to some degree?
No, I don't think so. But facts have caught up to their logic, though. They're asteroids that are dependent orbitally on several planets, including two small ones that are in Earth's orbit. So Earth, the planet we're standing on, hasn't cleared its orbit of all the debris.
Oh,
which
right. That was one of the definitions.
One of their criteria, their third and weakest, most illogical criterion, right? So those discoveries happened in 2010 and 11 after the IAU demotion, which, by the way, was done by astronomers, not planetary scientists.
Right.
It was done by the astronomers who were left on the last day of the convention.
That's right.
As I recall, they were supposed to vet new motions through a committee before they were brought to the floor, and that was not done when the second motion was made. So,
and dwarf planets are planets after all, just like giant planets are planets. And Pluto doesn't care what you call it. It's pretty cool.
Oh, that's way cool. That's way cool.
I
Well, they're
think
all
Pluto
worlds,
cares.
right? They're all amazing worlds.
I think that flew over Scott's head.
It probably did. Many things do. Got a hole in my glove.
Got a hole in my glove.
Yeah. One of my favorite cartoon characters is Foghorn Leghorn.
Oh yeah.
you must have loved that ad.
Boy, I said boy.
Oh man.
Yeah. Actually, Wile E. Coyote. When I was young, I didn't understand Wile E. Coyote. I thought it wasn't funny, but then when I got older, it was like he's hilarious.
Yeah. He's the straight man. Somehow. The buffoon.
Yeah,
The
does everything right.
I like the Tex Avery cartoons also. Those are good.
Yeah. My daughter's favorite cartoon is one with Daffy Duck in it, and Daffy Duck is told by his nagging wife to sit on the egg while she goes out.
Oh yeah, I remember that one.
And he does this magic trick where he makes the egg disappear,
Yeah.
And he does it, and he shows it again, he shows it again, he shows it again, and finally he does it one more time, and the egg disappears. He can't get it back, okay?
Yep.
And now the wife's coming home. And he grabs a doorknob, yanks it out of the door, sets it in the nest, and then sits on it. But before he does, the doorknob turns up, and anyways, he kind of gets shafted. It's pretty hilarious.
That's a kid's cartoon.
It's a kid's cartoon. It's and it's my daughter's favorite cartoon of all time. They've been watching it since they were little. Well, we got a nice group of people watching us right now. We got James, the astrophotographer. Pekka's in the audience right now watching, but he'll probably log on later. Chris Larson is on. He says, "What up?" We got Harold Locke. Good evening. All hello. And Steve Hauser. Good evening from cloudy Idaho. And we got Ottavia Zorzi, looks like. Good evening from Italy. It's fun to see people from around the world watching. Pekka, we know he's from Sweden, yes. And Steve Hauser, my 8th grade algebra teacher, was Percival Lowell's grandson. Wow. That's cool. Wajdi Zara says hello to everyone. Martin Eastburn says, made it again, and howdy, everybody. Jeff Setzer, dwarf planets are not planets. Uh-oh, okay. He's drawn the line. Chris Larson is watching. Aaron Thompson's watching. Says, greetings.
Aaron.
Yes, Setzer, my English teacher family doesn't like that. Okay. Wajdi says it's 1:52 in the morning in Tunisia. That's pretty early.
Or late, depending on how you
Or
look.
late. That's right, depending on what's going on. Mike Wiesner's on. Hi from Southern Arizona. Gary Albin says hello. And Jim's Astro says hello. And Aaron Thompson says hello. So, more to come.
Looks like we have a nice group tonight, all over our global world.
Yes. And for all of you watching and participating, if you can share and like and ring the little bell and subscribe, it's very much appreciated. By the way, and I've cleared this with the Solar System Ambassadors group, all of these programs will be included as Solar System Ambassador events. So tonight, including Molly Wakeling, who I know is a Solar System Ambassador. I think we've got one or two more here, including myself. We're on the program. And so we got a nice visualization from NASA at the beginning of the program. It kind of goes along with David Eicher's talk about black holes, which is going to be cool.
David looks like he's getting ready to look through his telescope.
Who, me?
Yeah, you. It looks like your ear was right next to the eyepiece. Maybe it's a radio telescope.
You know, the scope in back of me. Yeah.
Yeah.
You know what I just found? I have to read this quotation now. I found a quotation in I've completely forgot about this, in the frontispiece of this New Cosmos book. This is a funny quotation, but I'll save it for when I start. From, of all people, Alfonso X of Castile, our old friend, 1221 to 1284.
I'm not sure, but I think he's dead now. What do you
An
think?
unlikely pick for a philosopher of science, but he was interested in it and has one great quotation about the complexity of the world. And yes, he is quite dead, just as Francisco Franco is still dead.
Yeah. Hello, John W. Briggs. Good to see you.
Tom Briggs in the house.
I think we've got an interesting evening ahead of us.
John is in the house.
John's in the house.
Hi, John. He's muted. He's in the house, though.
Yeah. So Gil Clark contacted me about a bunch of telescopes and astronomy equipment that he has and wanted it to go to a museum. And I could think of no better museum than the Lyceum with John Briggs. So I think they're going to be able to connect, and he will add to his huge collection. We're going to have a big meeting at the Lyceum sometime.
Yes, Star Party in New Mexico, huh?
New Mexico at the Lyceum.
Yeah.
Mm-hmm. I'll bring entertainment
Big meeting.
of some sort.
I thought you were the entertainment.
Ooh.
Hmm. This is cool. Well, hello everybody. This is Scott Roberts from Explore Scientific, and this is the Explore Alliance presentation of the 43rd Global Star Party. And we have a great group of astronomers with us right now, and more to come. It is, it's always a great pleasure of mine to be at the Global Star Party and to see the audience from around the world, and to have participants and presenters from around the world as well. And so it makes me realize that this is why I do what I do. I love this. So we will have a great schedule today. We've got David Levy, of course, who'll be up first. David Eicher, who's going to talk about black holes. Molly Wakeling, about how energy is made in the sun. John Briggs, who talks about his long night at Amundsen Scott South Pole Station, Antarctica. That's going to be very, very cool. We had some conversation about that before we started today. Libby and the Stars.
It'll be cold.
It's cold there. Libby and the Stars is with us. Chuck Allen from the Astronomical League will be conducting door prizes, but he's going to do double duty tonight because he's also going to give a lecture. By the way, I mentioned Molly Wakeling. She's doing double duty too because she's giving a lecture first and then live astrophotography last. So that's cool. Pekka Hautala about making the skies darker in Sweden. he'll be with us. Then we'll take a 10-minute break. Jerry Hubbell's going to be on with some astrophotography, if it's clear. Adrian Bradley, a program about Moonrise. And Chuck Allen's talk, and then Molly Wakeling's astrophotography. And then our after party starts. So if you're interested in the after party, I've already included the waiting room link. So you just have to kind of wait until we get towards the end of our speakers, and then you can log in and share the experience with us. But right now, we're going to turn our focus onto David Levy, a friend of us all, a man who almost never says no to supporting astronomy and doing astronomy outreach. I think the only time he says no is when he's actually doing astronomy outreach someplace else. So, but he's an amazing guy, a huge inspiration to a lot of us, and one of my very best friends. David, I'm going to give you the stage.
Thank you, Scotty. And I say no tonight. I'm not going to do a quote, and I have nothing to do with tonight's star party. Are you okay with that, Scotty?
I'm good. I'm fine.
No. Okay, I can't. You're right. I cannot say no. It is not in my DNA. The words don't exist for that. Anyway, while we were all waiting, David Eicher and Jerry Hubbell and Chuck and Libby and John and Cameron were talking about certain things that were kind of entering our minds. And one of them was Abraham Lincoln. And a very interesting story that took place. It appears not to be apocryphal because I've read it in a printed book about Asaph Hall, who one night in 1862 was observing at the old Naval Observatory. He was in a terrible mood. Things were just not going right for him. And then there was this knock at the door, a fairly soft knock, and he just blew up. He said, I'm going to open this door and I'm going to scream at whoever it is, tell him to leave me alone, not to bother me. And so he went down the chute, down the stairs, and opened the door. And there, all by himself, standing there, was Abraham Lincoln, President of the United States.
Wow.
No security. He was just there by himself. And he said, I'm sorry to interrupt you, but I've had a horrible day, as it looks like you have. And I just wanted to know if it would be okay if I took a quick look through your telescope. And Hall was ready to yell and scream, and he opened his mouth and closed it, and he goes, and he says, you're welcome here. Yes, they had a wonderful evening. But I think the best part of it was that, Lincoln knew about the telescope. He asked intelligent questions like about how telescopes invert the image, which is one of the most basic questions. But at the very end, he said, almost like a little child would ask, can I come back again? And Asaph Hall said, you are welcome here anytime. 2 or 3 nights later, he came back with his Secretary of War for a second evening. Anyway, that brings me to a story that I have to share. 27 years ago, I and Jean and Carolyn Shoemaker were at the White House to celebrate. Actually, it was the 25th anniversary of the moonwalk by Armstrong and Aldrin and Collins. And we were there, and the afternoon was getting over, and we were about to leave when someone came in and said, excuse me, but the vice president wishes to discuss something with you. Would you mind waiting a few minutes? And Jean looks and says, well, I'll have to check my schedule. And, oh, of course we're going to wait. Of course we will. And he appeared. And, as he was talking with us, and it was more of a conversation of a group of enthusiastic amateur astronomers than it was a conversation about politics or anything else. And I'm thinking of this in the back of my brain, and I'm thinking, well, you can say what you want, but I'm going to get to look at the impact spots before you are. And then it happened. He said, you know, I live on the grounds of the Naval Observatory. And I thought to myself, don't say it. And he said, and the other night I said, please don't say it. I went to the observatory and I asked if I could take a look at the impact spots. And they showed them to me. And I said, you beat me in my own game. You got to see the spots before I get to see them. And he says, well, that's the way it should be, isn't it? When you become vice president, then you can look at the impact
you can
spots
do
first. Anyway, it was a lovely, lovely story. I have two little quotes for you tonight. And the first one is from Connaissance du Temps, published in 1801. And it's by Charles Messier. What caused me to undertake the catalogue was the nebula I discovered above the southern horn of Taurus on 12 September 1758 while observing the comet of that year. The nebula had such a resemblance to a comet in its form and brightness that I endeavored to find others so that astronomers would not confuse these same nebulae with comets just beginning to shine. It's a very famous quotation, almost as famous, not quite as famous as this one, which I'm going to conclude with. This one is from Hamlet, and it's one of the most famous quotes in all of that play, but it was made a little more famous when Patrick Stewart uttered it on a recent on a Next Gen episode. This most excellent canopy, the air, look you, this brave or hanging firmament, this majestical roof fretted with golden fire. What a piece of work is a man! How noble in reason, how infinite in faculties, in form and moving, how express and admirable, in action, how like an angel, in apprehension, how like a god, the beauty of the world, the paragon of animals, and yet to me, what is this quintessence of dust? And on that note, I give it back to Scotty. Thank you.
Thank you, David. Thank you. You know, it's always an honor to introduce each one of these people here. But I often like to work with others to give that honor to other contributors to our community of amateur astronomy and for those who like to participate in Global Star Party. Next Global Star Party will be, our special guest host will be Cesar Brolo from South America. So I expect to see a lot of interesting people from his I'm not going to say his neck of the woods, but his area down under. And you know, one of the people that that I was also very honored to hand over the Global Star Party to was Dave Eicher and his whole group of editors from Astronomy magazine, and that was amazing. I don't know if that's ever been done before, but it was a beautiful thing, and you know, but everybody, including, I mean, David Levy and others, Jerry Hubbell, who will also be on tonight, and Molly Wakeling, who's been on tonight or will be on tonight, have all done this. But I think that seeing all those editors there, sharing all their knowledge and everything, that's going to stick with me for a very, very long time, maybe forever. David, thank you so much for coming on all these programs, and I look forward to your talk tonight.
Thank you, Scott. We'll have to do that again sometime with the editors. They'd love it, I think.
It was great.
Thank you, David, for inspiring us always. And when David, a little while ago, when we were bantering around before we got started here, we were talking about this and that. David always has fantastic quotations, of course, that he shares with us. And I stumbled on one. I forgot that I had these in a book that I had done some time ago. Here's one that I always thought was a great outlook on the universe. Now, this was from Alfonso X of Castile in the 13th century. And his quotation about the universe when his scientists of the day, this is 800 years ago, were trying to explain how it all worked to him. His reply was, if the Lord Almighty had consulted me before embarking on creation thus, I should have recommended something simpler. And I think a lot of astrophysicists would agree with that as well. But on that note, I wanted to talk a little bit tonight about black holes, one of our favorite subjects of all. Because for such...
Quote, David.
I'm sorry, David?
Was a wonderful quote. Thanks for sharing that with us.
Oh, thank you. Of course. Yeah, you bet. Yeah, that's quite funny for such a long time ago. I think that, and for a non-scientist head of state, if you will, to say, yeah. Black holes have fascinated, I think, all of us, all the way from the origins of thinking about what the stars were in the night sky back then, a millennium ago, up until more recent times. And it's funny because even at the time when I came to Astronomy magazine in 1982, black holes, in some sense, were still largely a rumor. There was a tremendously slow accumulation of evidence for black holes and their existence. I think the best quotation about black holes of all comes from our Starmus friend, who's a wonderful guy, very generous guy with his time, Kip Thorne. Black holes are the brightest objects in the universe, but no light, Kip likes to say. And by that, he means that they're tremendously energetic. And of course, he was one of the co-creators, if you will, of LIGO, which, of course, as you know, a few years ago, detected the first merger of a black hole via gravitational waves. But they're very mysterious, and they eluded detection for a very, very long time because the concept of a black hole being proposed goes back about 230 years to the English natural philosopher John Mitchell, who studied gravity. And of course, at that time, essentially, most all scientists were called natural philosophers, and they had some degree of expertise in what we would now call several sciences. He proposed that there should be, with a very intense gravitational field, what he called dark stars that would be so gravitationally compressed that nothing, not even light, could escape. And of course, that turns out to be conceptually what black holes are. They're regions of very intense gravity in which nothing, not even photons, can escape. Little progress happened really in terms of any concrete progress until the time of about Albert Einstein in the early 20th century. We mentioned, we were talking about Einstein earlier, but he did some of his very serious mathematical work, of course, on the general relativity theory and its notions that space-time is warped rather than flat. And that led to a lot of investigations of the concept of black holes. His friend, Carl Schwarzschild, also did a lot of work mathematically on black holes. He died, sadly contracted a disease and died just at the end of the First World War. But a lot of the mathematical work that he did led to a brief time when the concept of black holes, they were called Schwarzschild singularities. Well, quite a number of astronomers later in the 20th century studied massive stars, of course, Chandra and many others, and predicted that they could collapse into black holes, stellar black holes that result from the deaths of massive stars above a certain mass limit. And it turns out to be more or less 10 solar masses, 10 times the mass of our sun. But no one knew of a single one, of course, as a concrete example for many, 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 many years. In fact, it was 1975 when a radio and other emission object that came to be cataloged as Cygnus X1 became a prime suspect for a stellar black hole. This was the late 1960s and early 1970s. And by 1975, another famous theoretical physicist entered the realm, Stephen Hawking, who we, as you know, we just lost a few years ago here. But he had a storied career, just carrying on what Einstein had done at the back end of the 20th century and the early part of the 21st century. Well, Stephen Hawking and his friend Kip Thorne, they did a lot of work on what black holes should do. Kip Thorne's book is a great book still, even though it's a little bit old now, Black Holes and Time Warps. That's a book that if anyone is interested in black holes, they should have in their library. You can get a good paperback edition of that very easily now. Well, they ended up making a bet. They thought that Cygnus X1, this very high energy, what appeared to be a dead star, would turn out to be a black hole. But for fun, they made a bet against each other. This was in 1975. Just for a kick, Hawking bet against Cygnus X1 turning out to be a genuine black hole. And his friend Kip wagered that it would turn out to be a black hole. Well, it turned out that it took 15 years to get the verifiable evidence published in papers that Cygnus X1 was incontrovertibly a black hole, a stellar black hole. So Kip won the bet. Hawking wagered that if he would have won, he wanted a subscription, 1-year subscription to Popular Mechanics. And Kip wagered a little more daringly that he wanted a subscription to Penthouse. So Stephen Hawking bought a subscription to Penthouse and sent it to Kip Thorne at Caltech. This is a very famous story. It actually happened. But it tells you how incredibly long it took to really verify the existence of any single known black hole of the quite a number of candidates that existed by that time. However, then the doors opened, and just a couple of years by the time the Hubble Space Telescope was fixed, its optics, there was a bonanza going on with looking at galaxies, extragalactic sources. And there were lots of people working on this, but John Cormandy at Texas and his collaborators, Lewis Ho and others, started finding lots of supermassive black holes in the centers of galaxies. And the rotational velocities of gas and of stars basically made it such that no, there couldn't be another explanation but a supermassive black hole. So by the early to mid 90s, it became clear that the Milky Way, that the Andromeda galaxy, that M106, and that lots of other normal galaxies had central black holes as engines in them, and that this was very common. In fact, now it's known that it's believed that essentially all normal galaxies have a central supermassive black hole, except for dwarf galaxies, which don't have the mass to have supported them. And they also grow and evolve essentially in tandem with the mass of the galaxies over time. Although, of course, they go quiet later in their evolution as they run out of stuff to eat, if you will.
Hey, David, I got a little bit of a side question. You mentioned dwarf galaxies.
Yes, sir.
I'm sorry? Are dwarf galaxies really galaxies, just like dwarf planets aren't really planets?
Dwarf galaxies are really galaxies. Most of the galaxies in the universe, from what we see from local groups and clusters, are dwarf galaxies, just as most of the stars in our galaxy are dwarf stars. Red dwarf stars outnumber normal, what we would call normal stars like the sun, by a large factor. And the same is true of galaxies. There are at least 55 galaxies in the local group. There are probably a lot more, though, because a lot of dwarfs are obscured by the Milky Way and so on. There could be as many as 100 galaxies in the local group, but let's call it 55. Well, there are three big spirals, the Andromeda galaxy, the Milky Way, and M33, and most all of the rest of them are dwarfs. So that gives you an indication of how dwarfs outnumber larger galaxies, and we think that's typical of galaxy groups and clusters. And for example, the vast majority of the 400 billion stars, maybe roughly in the Milky Way, are red dwarfs as well. So it became clear that most galaxies have a central supermassive black hole. And not to go on forever about this stuff, but there was a whole generation later, it became clear that all the kinds of crazy high energy galaxies, active galactic nuclei, which were thought to be lots of different kinds of weird distant things at first, Seyfert galaxies and BL Lacerdae objects and so on and so forth, are all galaxies that are powered by central supermassive black holes. So quasars are the very young, very energetic galaxies that have a lot of emission coming out of their active black holes. They quiet down later on in their evolution, generally speaking. So supermassive black holes are the norm in the centers of galaxies, but they're not universal. For example, M33 has no favorite but somewhat difficult galaxy to observe, low surface brightness, but close by spiral to us in our local group. It does not have a central supermassive black hole. So there are exceptions, but most all normal galaxies have them. Stellar black holes, however, although the first one, they were hypothesized as that almost a quarter of a millennium ago. And the first confirmed black hole was a stellar black hole. We know how stars evolve very, very well. But stellar black holes remain to be extremely elusive. They're very hard to see. You have to see them interacting with a relatively close, bright object. So there must be millions of stellar black holes in the Milky Way galaxy, but we know of any guesses in the Milky Way of how many stellar black holes we know of now? Does anyone want to venture a guess?
0 still?
About 24. Cygnus X1 being one of them. So we found a couple dozen out of what must be millions of them in the Milky Way.
I'm surprised it's so few.
They're hard to see, hard to detect. So just to end quickly, I don't want to ramble on forever here, but there is an important question that must be asked, and this is something that fortunately with their involvement with Starmus, I was able to be involved in hearing Stephen Hawking and also Kip, who's still with us, talk about, could you fall into a black hole and survive? Well, this is the staple of practically all of science fiction. You know, who wants to crush the hopes, dreams, and aspirations of every good sci-fi movie, or bad movie for that matter, ever made? Well, you know, we have to, because we're living in reality here.
Oh.
So the interesting, but it's different. It's different than you might think. The interesting part is the gravitational effects. If you fell into what's called the boundary, the so-called event horizon of a black hole, a stellar black hole would pull you into a string of protons that would be something on the order of 10 kilometers long, your body. So there's been a lot of talk, of course, of wormholes, of going into a black hole and coming out in a different place and time in the universe, and using that as time travel. The most distinguished theoretical physicists, including Hawking and Thorne, have all written about that. It's not a lunatic idea from a mathematical perspective, but a stellar black hole would pull you into a string of protons. So that kind of ruins your weekend, regardless of where you're headed. With a supermassive black hole, you could actually pass through the event horizon without even feeling it, without even knowing the G-forces that you're inside a black hole, briefly. But then in both kinds of black holes, and this goes for a third type, intermediate black holes as well, which we don't need to get into, but the singularity at the center of the black hole would then crush you into a microscopically small particle. So realistically, traveling around and going to places and using shortcuts with black holes to get to different and new Star Trek episodes isn't going to work. But it's a fascinating thing to think about, the physics and the mathematics of that, and what would happen if you actually do get close to a black hole. It wouldn't be good.
Is there I've read some over the years about white holes being like the opposite side of a black hole. Is that kind of part of that theory?
Yeah, white holes, wormholes, and again, that's all hypothetical, and it is grounded in some sensibility what may happen, but again, mathematical possibilities and real logistics in the real universe are different things. It's also there's some serious talk, just to raise a quick analog about the black hole, wormhole, white hole business. There's also talk relatively recently about, this business of multiverses, of how we could hypothetically be in one universe among many that are in, if you imagine the large scale structure of super galaxy clusters that are in fibers and have sort of bubbles between the fibers, like soap bubbles. Could we be in a universe of many? And the conventional answer there is, well, maybe mathematically, and we'll never know, because by definition, the observational universe is the one we're in and we can't see or detect beyond it. But there is actually some talk relatively recently from people about maybe there could be some mathematical signatures from other universes that you could detect somehow, someday, maybe. It doesn't seem likely. I wouldn't wager my house on this, or life savings. But and the same goes for black holes as travel mechanisms. I think these are academic exercises for the mathematics, but in the real universe, you couldn't do that anyway. And the distances to get to them anyway, realistically, would require significant fractions of all the energy that exists in the universe to move things like us with mass over many, many, many light years. So it's all, academic, if you will, hypothetical, but it's fun to think about.
Yeah. So my brain is wrapped around some event horizon right now. So,
well, I do really, Stephen wrote some great books that talk about this a lot, but even though it's been out for a while, Kip Thorne's book, Black Holes and Time Warps, if you're interested in this stuff, is essential. Okay. That's really, if you really want to have your mind blown, from the surviving master of black holes, he's the guy who can entertain you. Yeah.
Maybe one day I can wrangle him onto our show. He's huge inspiration, and I've had the chance to meet him one time during the 2019 eclipse in Chile. So he's a real gentleman. So
he's an extremely nice guy. If you go to Starmus, you should be able to meet him there.
Yeah, well, I will definitely go to Starmus. So I'm going to make a recommendation to read some books here. We have some, a book I often show here during Global Star Party is David Levy's autobiography, A Night Watchman's Journey, which you can get on starzona.com. It's a great account of his life. And then we have, very appropriate for this talk, is David Eicher's book on galaxies, which is dedicated to Brian May, who's also a good friend of David's and is a huge supporter of Starmus. In fact, I have another book here too, which is Cosmic 3D Clouds, which I've shown on a few of these Global Star Parties, but this is co-authored by David Eicher and Brian May. And then later on, we're going to have Jerry Hubbell, who is the guy that manages the Patrick Moore Practical Astronomy series, and this is one of his books, Remote Observatories for Amateur Astronomers. If you're interested in astrophotography, he also has a great book on scientific imaging. So, up next is Molly Wakeling. Molly, I believe you are a solar system ambassador. Is that correct?
I'm actually not, but
you're not.
no,
Oh, you should be.
I should be.
You should be. You should be.
I need somebody to nominate me.
Yeah, I can think of a few people here that would do that. So, Molly's presentation, often she comes on our program and sprinkles in grayed out live images that she's taking from her backyard full of telescopes. But she, on occasion, she gives also a nice presentation, and this time it's about how energy is made in the sun, if we're still on that topic. So, Molly, thank you for being a great supporter of Global Star Party, and it's an honor to have you on our show.
Thank you. Yeah, I like coming on here as often as I do, and it's nice to do some scientific presentations on occasion as well. Though I really do also love sharing views from my backyard telescopes, which I'll also be doing tonight because it's going to be clear. So awesome. Hang out for some live views. I'm going to show M81 and M82, I think, on my color camera. So
okay.
All right. Well, let me share my screen. All right. You should have my full screen version.
Yep.
Okay. Yeah. So I'm working on my PhD in physics, and so I like to, when the opportunity arises, give some scientific talks at STEM events and stuff like this. That kind of dig a little deeper into the physics of stuff in space that we see all the time as astronomers. So I gave this talk the dramatic, undramatic title of How the Sun Works for fun. All right, so the kind of outline of, sorry, I'm gonna close my window here. Some noise coming from outside. The outline of kind of how the sun works basically is hydrogen fuses into helium, energy is released, and that energy eventually works its way out of the sun and makes its way over to us. But there are some really important things to understand in each of these steps that you might not think about on first glance. For example, hydrogen is one proton, and helium is 2 protons and 2 neutrons. Where do the neutrons come from? I say that energy is released in this reaction. What kind of energy? And the energy works its way out. How does it work its way out of the sun? And what's making that difficult? So in order to get into the exact process of what's happening in the sun, it would be beneficial for me to cover a little bit of particle physics to kind of whet your appetite on that. So so you're familiar with the idea of atoms, and at the center of an atom is the nucleus, which is made of protons and neutrons. And when they grab onto electrons, they become an atom. And that's what makes up anything and everything that we interact with ever in our lives, for the most part. So when it comes to the atoms, make up the elements in the universe. So if you have one proton, then that is a hydrogen nucleus, and then when it grabs an electron, it becomes a hydrogen atom. But now the sun is very hot, so I'm going to pretty much ignore the electrons from here on out because they all have evaporated off of the atoms inside of the very hot sun. So really we just kind of have protons flying around. Helium is the next in the periodic table. It has 2 protons and 2 neutrons. Lithium is next with 3 protons and 3 neutrons. And this pattern continues, kind of. So you don't have to go very far before you don't have the same number of protons and neutrons anymore. Fluorine has 9 protons and 10 neutrons. Iron has 26 protons and 30 neutrons. And then the heaviest naturally occurring element is uranium with 92 protons and 146 neutrons. And the reason why these numbers start to vary is because protons are charged particles. And sort of like when you try and push 2 of the same end of a magnet together, 2 like charges also repel each other. So protons, they can't hold together. They need some glue to hold them together. And that's what neutrons do. And the more protons you get, the more neutrons you need to hold those protons together. So that's why the number of protons and neutrons kind of starts to diverge a bit. And from there, you get the entire periodic table of elements with each one labeled by their number of protons, and each having not only one variant of how many neutrons they have, but oftentimes several. That's where you get radioactive elements and things like that that have extra or fewer neutrons than is stable. So I'm not going to get into radioactivity in this talk. Maybe I'll have to do another one about radiation. That'd be fun. So let's talk about how hydrogen fuses in the sun and how we get to helium from there. Because it's not as straightforward as two protons coming together and neutrons coming from somewhere. There's a couple of steps involved here. So first, you do start with two hydrogen atoms, or really just two protons, because it's so hot inside the sun, the electrons are not there. They're not attached to the nuclei. And a process called beta decay occurs because diproton, having two, or dihydrogen, having two protons together with no neutron, they won't stay together. So one of the protons actually converts to a neutron in a process called beta decay. And beta decay emits an electron and a neutrino, and you get deuterium, which is it's hydrogen with a neutron. It's heavy hydrogen, and that's what heavy water has in it. So that's the first step, is you have these two hydrogens that become a deuterium. And then a third hydrogen comes along, a third proton, and attaches to, fuses with the deuterium, with the deuteron, and becomes helium-3. And that fusion reaction actually releases energy in the form of a gamma ray, and I'll get to what that is in a bit. So now we have helium-3, but we're still not to helium-4, which is what makes up the majority of the sun's contents. So the next step is two heliums come together, two helium-3s, and those form a helium-4, which is the common isotope of helium. And if you count up the protons and neutrons, you'd see that in order to get to helium-4, we have two extra protons left over in that reaction. And those go flying off to go form more deuterium and helium-3 and eventually helium-4. And we get a lot of energy out of that reaction. So this is where the bulk of the energy in the sun is coming from, is this series of reactions known as the PP chain, or proton-proton chain. Now there's a continuation of this called the PP chain 2, where you have a helium-3 from the PP chain and a helium-4 from the PP chain, and those two fuse together to become beryllium-7, and that also emits some energy, although not as much as the two helium-3s coming together. From there, the beryllium-7 can capture a free electron and beta decay, basically inverse beta decay to actually no, it's electron capture, and you have a proton that converts to a neutron. So now you're back to lithium-3, and you get a neutrino and some energy out of that reaction, but not a whole lot. And then that lithium-7 can grab a proton and very briefly become beryllium-8. But beryllium-8 is really unstable and does not naturally occur, really. So that immediately falls apart into two helium-4s and a ton of energy, even more than PP chain 1. But this reaction occurs less often than the other one. So with the energy, there's some other processes that also produce energy in the sun by fusing hydrogens and heliums and lithiums and things like that. But they're much less common and doesn't really make up the bulk. So I won't go into it here. When I talk about energy being released, and I give it in this weird unit of MeV, which is mega electron volts, what kind of energy are we talking about here? So this would be a good time to bring up the electromagnetic spectrum. So we typically think of light as the visible light and the stuff you can see, sunlight and lights like lights in your home, lights from your computer screen, whatever, the stuff that our eyes can pick up. But there's a lot of other wavelengths of light that are things you're also familiar with, but maybe didn't realize were also light. Radio waves, for example, are a very long wavelength of light, where the distance from peak to peak of the wave of light is measured in meters. And then you have what your microwave uses in between radio and infrared on this chart. And that's on the order of a centimeter in wavelength and very low energy. Then you get to infrared, which is like what your TV remote uses to communicate with the TV. And that's also like if you have an infrared lamp, you'll feel some heat from that. And then you have the visible spectrum, and then we go up into ultraviolet, which is what the part of the sun spectrum that burns your skin if you stay out too long, X-rays, and up to gamma rays. And gamma rays are extremely short wavelength, extremely energetic wavelengths of light. And that's what we're talking about here with the energy that is emitted from fusion processes are typically gamma rays. Now, there's a little confusion between nuclear physics and basically every other kind of physics, where we have this definition of gamma ray as specifically being this very short wavelength of light. But in nuclear physics, a gamma ray can be any wavelength of light that is emitted by a nucleus. A gamma ray could be infrared or visible or even radio. We don't typically have radio gamma rays from nuclei because they're too low energy. But yeah, so that's a confusion of terms to keep an eye out for. But here we are talking about both. We're talking about a gamma ray that is of gamma ray energy.
Right. So that's something I'm been in the nuclear field for a long time. So they basically lump together X-rays and gamma rays together is what they do in the nuclear world. And when you're explaining it.
Yeah, because a lot of gamma rays are of X-ray energy. But then in order to differentiate from characteristic X-rays that come from high energy electron transitions and stuff like that as well. So yeah, it's a bit interesting how those two terms cross each other. But yeah, in nuclear physics, we typically anything that comes out of the nucleus is a gamma ray, even if it's not of gamma ray energy. It's a fun time. All right, so finally, how does that energy that is created in fusion actually make its way out of the sun? It doesn't just get created and then head towards the outer edge of the sun and then out of the sun. There's a lot that happens in between because there's a lot of mass in the sun, and light interacts with matter, just like how you can't shine a light through a wall. So what's happening here is so energy is produced in the core from those fusion processes. The next layer up is the radiative zone, where there's no thermal convection. So you're not passing along heat like you would in your oven or through the air, but atoms are so densely packed that they're actually absorbing and re-emitting that light as the light tries to travel through. So it's going all different directions in this random walk. And it's actually, the light is slowly losing energy as it's being absorbed and re-emitted, and there's some energy loss in that process. Above that is a convection zone, where atoms are not completely ionized, aka they have some of their electrons instead of having none of their electrons, which further slows the process of a particular photon of light getting out of the core, because they're even more likely to absorb photons because electrons can absorb them in addition to the nucleus. And then in the convection zone, you have cooler material dropping to the bottom and becoming hot again, and then hotter material rising, and you have this continuous convection process that moves material around. Then finally, once your photon makes it out of that mess, it gets up to the photosphere, where the light is emitted out into space. Now, on the chart here, you'll see that the photosphere is much, much cooler in temperature than the core. And that light that was originally a gamma ray is now most likely to be a visible light photon. That temperature corresponds with green, which is the peak wavelength of the sun. But because of the way the spectrum is shaped, this Maxwell-Boltzmann distribution, as we call it, it actually ends up appearing white because it's covering all the visible wavelengths that we see, not entirely evenly, but enough that it appears pretty much white. And then, of course, as you see here, the chromosphere and the corona are much hotter than the surface of the sun, and we don't actually know why that is yet. That's one of the things we're hoping to learn with the Parker Solar Probe. So trying to kind of solve that interesting mystery. So some fun numbers to leave you with at the end here is, you look up at the sun and yeah, it's hot, and yeah, it's big, but how big? And how massive is this relatively small star in comparison to some others that we've seen? So so I mentioned how long it takes, how difficult it is for light to get out of the core. Well, it takes 10,000 to 100,000 years for a given photon to actually escape the core. So it has to go through all these emissions and absorptions and re-emissions. It knocks into all kinds of atoms and nuclei, and eventually, tens of thousands of years later, makes it to the surface of the sun. But there's so much mass in the sun being converted that there's so many reactions happening that it is outputting continuously, and putting out a lot of energy, even though it takes this long for a photon to get from the core to the surface of the sun. The sun fuses 600 million tons of hydrogen every second, and 4 million tons of that is converted to energy. Some of it, we have electrons and neutrinos and other particles, protons going out, but a lot of that is converted directly to energy. The energy output of the sun is a unit. There is an SI prefix called yata, which is 10 to the power of 24. So the sun outputs 384.6 yottawatts, which is 3.8 times 10 to the 26. So that's 3.8 with 26 zeros after it.
Should be a lot of watts.
Yeah, it's a lot of energy. And to put that into another unit, it's 90 billion megatons of TNT per second. So that's like 40, let's see, that's like 4 billion Tsar bombas, the largest nuclear weapon ever detonated on Earth per second.
Per second.
So it's a lot of energy. The sun is approximately 4.5 billion years old. Its lifespan for this type of star is about 10 billion years. And as far as how it compares to the Earth, it's 330,000 times the mass of the Earth, 1.3 million times the volume of the Earth, and 109 times wider than the Earth. So it's pretty big. Big enough that the center of mass of the solar system is still inside of the surface of the sun. It's just got, it dwarfs the, everything else is, all the other mass in the solar system is dwarfed by the amount of mass in the sun. So with that, are there any questions?
Yeah, I do, Molly. I wanted to ask you about the process by which the nuclei are held together. It's my understanding that the strong force is the force that actually holds the nucleus together, and that and correct me if I'm wrong, this is what I'm asking, that the role of the neutron is to keep the protons a little bit further apart to reduce the electrostatic repulsion and allow the strong force to do its job over the short range. Would that be correct?
Yeah, so the strong force is what's holding those protons and neutrons together. And essentially what's happening is the quarks inside of those protons and neutrons are swapping with each other.
Right.
And yeah, so it's the strong force and the quarks within that's acting as the glue for the protons and the neutrons holding themselves together.
And I had a second question also. May I assume that in the radiative zone, and certainly in the convection zone, that you are dealing with whole atoms, and that the radiation is absorbed by the atom, raising the electron to a higher energy level, which then drops, re-emitting the radiation. It's then absorbed in another atom. Would that be correct?
That's right. Yeah.
So the ionized elements would be in the core.
Yeah, so the fully ionized elements are in the core. In the radiative zone and to some extent the convection zone, you have partially ionized atoms that have some of their electrons.
Right.
Or, you know, there's going to be a spread of some that have none and some that have all.
Great.
Yeah.
Thank you.
Yeah, that's exactly what happens.
There's some comments here from the group here. Book Davies is saying astronomy and physics are almost inseparable. You can look all night, but eventually you're going to want to know why.
Yeah, that's kind of that's why I like being a physicist who is also does this amateur astronomy, is because I can look at that supernova remnant or look at that planetary nebula and have some idea of what's going on there and the significance of it and how amazing it is that there's all these huge amounts of energy and force involved and distance scales. And whenever I do star parties and outreach events and stuff like that, I always try to sprinkle in some of those details, like what's going on in that planetary nebula,
right?
To kind of give some more context of like, here's this thing you're looking at and here's what it is and what we know about it. And sometimes, you know, why it's an interesting object. Some of these galaxies that we look at have some really interesting stuff happening in their cores, and they're studied a lot by astronomers. And what can they tell us about how the universe was formed or how our own solar system was formed?
Right. Jeff Setzer says, when I learned how long it took for photons to make it from the core to the surface, what we think of as the surface anyways.
Yeah,
I was blown away.
Well
I've been doing astronomy since the 1980s, but I've only learned about it maybe 5 years ago.
Yeah, I learned about it when I was an undergrad in one of my astrophysics classes of how long it takes light to get out of the sun. And I was flabbergasted. I really thought that, you know, it was made and just kind of shot its way out of the sun. But no, there's so much nuclear electromagnetic interactions that are going on as it's making its way out of the sun that slow it down and reduce its energy. And it's actually really hard for a given photon to get out of the sun.
Book Davies is asking, how do they estimate or how do they know how long it takes for a photon to get out?
So we know things about the interior of the sun that we've been able to measure, like the density of the different layers and the atoms and nuclei that are in each layer. And we know from laboratory measurements how, and also from calculation, like when a photon interacts with an ionized hydrogen atom, what happens? You know, how much energy is absorbed, how much is re-emitted, how likely is that interaction to occur? So we can take all those numbers that we know and apply some statistical processes and be able to determine statistically how long it would take a photon to get out of the sun with all that information.
Great. Let's see, any other question if you'd like to? Pekka's making a comment here. If you'd like to see IR light, you just need a full modified DSLR and look with live view or take a photo of a remote with a remote control, meanwhile pushing a button on it. Okay.
Yeah, actually, you can do that with your cell phone because they don't have IR filters on them, so that they can do autofocusing in darkness and stuff like that. So with your cell phone camera, you can see, if you point your remote control at the camera, you can actually see the infrared light, which is really cool.
That's cool. Wonderful presentation, Molly. Thank you so much. That's great.
Thank you. And I'll be back on later with some live telescope views. It's still daytime here, but later on it'll get darker.
Beautiful. Thank you, Molly.
Yes. So if you
Archer.
all are hearing what, are you hearing waves in the background? Because I forgot to mute the last time I dialed in. I'm actually out in the dark, and I thought of trying that, but there's just a lot of clouds around. But that's an interesting tip. I may try it before I leave here or before I actually do my presentation.
Excellent.
So,
Okay.
yep.
All right.
I
well,
will go back on mute.
All right, Adrian, thank you. And Adrian will be on later with his presentation about Moonrise at about, depending on how this program runs, about 10 o'clock Central. Up next is John Briggs. John has been on the last several global star parties, and his presentation, A Long Night at Amundsen Scott South Pole Station, is with us. I have the PowerPoint here, and so I'm going to go ahead and pull that up. But while I'm doing that, John, do you want to say a few words?
Well, yeah, just a few words. It was a great adventure of my life getting to go to Antarctica to operate some astronomy-related equipment at South Pole Station. And that was how I had a chance to get involved at Yerkes Observatory in Wisconsin. This was in the early 1990s. And so the pictures that you'll all see in the presentation, they're all historical now because they're the station at South Pole has changed a lot since 1994, but these pictures are still very interesting to see. And it was Center for Astrophysical Research in Antarctica that was funded by National Science Foundation and headquartered at Yerkes Observatory. And a lot of people have been going to South Pole Station ever since to pursue various specialties in observational astronomy. So go ahead, Scott, and let her rip. And if there are any questions at the end, I'll be happy to try to address them.
Okay, that's great. Here we go. All right. I'll bring that up. And bear with me here. Here we go.
Hello, this is John Briggs in New Mexico, and tonight I'm going to be sharing with you one of the great adventures of my life. Back in 1994, I spent a whole year living in Antarctica at South Pole Station. So tonight I'm going to describe to you the long night at Amundsen Scott South Pole Station. The project I was working for at the time was Center for Astrophysical Research in Antarctica that was headquartered at Yerkes Observatory of University of Chicago. And this was a center for science and technology supported by National Science Foundation. You know, trying to describe a year in Antarctica in 15 minutes is hard, especially because in reality, there were a couple of years work preparation even before my time spent there during the winter over. But it's mainly the pictures I want to show you, and so we'll get right into them and I'll move along. The aircraft to fly to Antarctica are LC-130 aircraft, and they are military transport aircraft. And here's a scientist looking out one of the few windows. It was an interesting experience. You travel to New Zealand and then you board the LC-130 in Christchurch, New Zealand. And then you fly to McMurdo Base on the coast of Antarctica. But before you land at McMurdo Base, you fly over some of the Transantarctic mountains and see spectacular glaciers like these. The crevasses down there, they don't look big in this picture from the altitude of the airplane, but the crevasses in the ice would have been big enough to swallow buildings and houses. were we beside them? Okay, here I am. The aircraft has landed in Antarctica, and it's interesting. You can see that there are skis that lower below the wheels. That is what is special about these particular LC-130 aircraft. They have skis as well as wheels. Then, of course, I'm trying to look cool there. And the glory days have long passed. These pictures were recorded now in the early 1990s. So this is a historical presentation as much as anything else. But of course, I was pleased to have this picture as a memento, and I showed it off to one of my engineer friends, and he said, "Oh, Briggs, at least maybe you could have buttoned your shirt straight." It was a 7-hour flight from New Zealand to McMurdo, and another 3 or 3.5 hours from McMurdo to South Pole Station. But by the time you get to South Pole Station, seen here with an aircraft landing, the topography has changed to what is like a frozen ocean. The altitude, though, is about 9,000 feet above sea level because we now are high on the Antarctic plateau. In '94, I arrived in early January, and you tumble out of the aircraft in appropriate clothing, and you head towards the center of the base, at least as it was then, and the sign says, "The United States of America welcomes you to Amundsen Scott South Pole Station." The geodesic dome, as I recall, was 160 feet in diameter at its base, and it was nothing more than a wind shield against blowing snow. The heated buildings were inside it, and they involved dormitory space, laboratories, kitchen and dining facilities, some administrative office space. It was quite a place to live for an entire year. Here's our winter over chef, Ed, standing in the inside circumference of the dome. Behind him is a chimney-like structure with a ladder that was an emergency escape exit. We'll see a picture of that from the outside later. And then piled all around the circumference of the dome in those cardboard boxes, food, profoundly frozen food. Here you see how wind-blown snow would tend to bury everything, including the big dome. But in the relative warmth of the Antarctic summer, diesel tractors could help keep it free from being completely covered by digging out around the circumference. Near the dome were these aluminum archways, long enclosures. In this case, they were housing fuel bladders that were about 25 feet or so square on a side. There's actually somebody lying down in the far right back corner of the bladder, second one in, and then further down on the right hand side, someone walking away from us under the line of lights, to give a sense of scale. The fuel in these bladders had been downloaded from aircraft and then used for powering the diesel electric generators all winter long. Compressing time tremendously, eventually the sun got near the horizon, and some of the buildings elevated on stilts cast long shadows like this. I was so hoping to see a long, lingering green flash phenomenon that's possible from South Pole Station if you're lucky enough to have the long extended sunset on a clear period. But unfortunately, we had clouds around the time of sunset, so no 45-minute long green flash that has been reported by observers on other years. So though it was stormy during our sunset, when the clouds cleared after several days, we were rewarded with a beautiful full moon and a twilight sky that then, of course, continued to last a long time because the sun remained only a little bit below the horizon for a long time. The entryway to the station main base that we saw earlier with the sign above it is now beginning to get encroached by blowing snow. And the temperature falls fast, sometimes getting to well below negative 100 degrees Fahrenheit, not counting wind chill or anything like that, but the true temperature down to as low as negative 106 Fahrenheit, in fact, in 1994 when I was there. Here's an outside view of that chimney-like emergency escape hatch that we saw Ed beside on the inside earlier. And this picture was actually taken well into the winter. You can see all the blowing snow. And it was, in fact, below negative 100 the day I took these pictures and walked around the dome. So, what's it like to go outside after months of lingering, fading twilight, and after it's become truly as dark as it's going to get at South Pole Station? Well, let me show you. Well, you step outside through that door, and the environment is very alien. With the wind-blown snow, it's as though you are at the bottom of a small crater on the moon or on some other frozen world. So up you climb to get out and look around. And the view above the crater is something like this. That's a gamma ray telescope there that was operated by University of Wisconsin. But you might notice the stars behind it, well, initially look unfamiliar. But the bright star immediately to the right, that's actually Sirius. And so you see the whole constellation of Canis Major there above Sirius in this case, because at least from our northern hemisphere perspective, everything in the sky looks upside down. And by the way, see inside the framework supporting the telescope, there's a central pillar coming up from the ground. Near the top of the dark central pillar, there is a pinkish object just to the left of the pillar. Pinkish because it's the Orion Nebula. This is a time exposure, so the stars are trailed. Remember, the belt of Orion is very close to the celestial equator, and the celestial equator at South Pole Station defines our apparent horizon on the celestial sphere. So the Orion Nebula is about negative 5 degrees or so, so it's about 5 degrees above our apparent horizon. And sometimes aurora is raining down all over the sky. We are actually inside what's called the auroral oval at a place like South Pole Station, so we don't see as much aurora as you might guess, but sometimes it was like this. By the way, the plume on the lower right is actually the exhaust from the diesel electric generator being illuminated by essentially an outdoor street light down there near one end of one of those long archways that I showed you before. One of my duties was to climb this meteorology tower to maintain microthermal sensors that we were using to measure air turbulence and thus understand the astronomical seeing at South Pole. And that's a Celestron 8 telescope set up there in the foreground. Here's one of my favorite self-photographs from my time there. I had been outdoors for maybe 3 minutes, but in such a short time, the humidity as I exhaled it, passing up by my eyebrows and eyelashes, well, it's natural for things to freeze very fast. The humidity in your exhaled breath freezes right out of the air onto nearby little hairs, and it was just the way it was functioning outdoors at South Pole. It was possible to use something like a Celestron 8 to estimate seeing, but only by using acetone to wash frost off the corrector plate. Because if you left the Celestron 8 out for a period of time, the changing atmospheric conditions, well, would just allow the buildup of frost. And we learned how to clean it with fluids like acetone that would not freeze. Here is the elevated laboratory building where we did most of our serious work. It's elevated to allow wind-blown snow to pass under the structure and not bury it so quickly. We had built a 24-inch aperture infrared reflecting telescope at University of Chicago, and here it is covered over by a fold-away tent-like structure. We referred to this as the baby buggy cover. Here the baby buggy has been folded down to expose the 24-inch reflector. It looks like a daylight shot with Sirius in the background, but it wasn't. This is a time exposure, and that Sirius is, what it looks like Sirius, is actually bands of aurora.
Cool.
Among our goals in '94 was to measure the brightness of the sky in the near infrared. But it was a wonderful coincidence that that same year, '94, a comet Shoemaker-Levy 9 crashed into Jupiter. Now, looking at Jupiter with the 24-inch telescope, the disk of the planet did not shine that brightly. So here are 6 exposures. The 2 moons, Ganymede and Io, are shining brightly in the near infrared, around 2.3 to 2.4 microns wavelength. The disk of Jupiter is quite faint, but there's a spot on it labeled G, and that was residual thermal energy from comet fragment G having hit the planet. But we were feverishly taking exposures about once every 30 seconds as we anticipated the arrival of fragment H. And so as you proceed from the upper left to the right and then across the bottom from left to right, you're seeing how fragment H came in, so essentially on time, releasing terrific thermal energy that dissipated slowly as the next couple hours went by. My good friend, Mr. Kerry Vigue, was the station electrician that year, and you see him here dressed up to spend a good chunk of time outdoors. And here's what he looks like having come back inside maybe 30 or 40 minutes later. He had been outdoors with a team of people looking for big packages that had been dropped for us by parachute as part of the midwinter airdrop. Fresh food, letters from home, all kinds of things were dropped one day, and it was a real special and exciting day for those of us, about 27 of us in '94, stuck at South Pole Station. Here's one of my teammates in the Kara project that year, John Kovac, and he is with the complicated apparatus for his microwave radio telescope. The device he has there before him is actually pointed downward, looking at a tray of liquid nitrogen as a calibration source. What he has there is the detector for his radio telescope that was designed to look at the cosmic background microwave radiation. Here's our other teammate, Hien, and John is smiling because he had been working very hard all through the winter to make this apparatus work right, and it was a challenge given the difficult environment outdoors. Here's a team carrying John's adjusted bolometer out towards the radio telescope. This structure was actually the enclosure for the radio telescope, and it was called the Sky Shield. The microwave radio telescope was a smaller apparatus at the heart of the shield, and that's John down there working on it. He spent a heroic amount of time outdoors that winter making this apparatus work, learning how to make it work. He has since become a professor at Harvard University. But finally, the sky was beginning to brighten. Months had gone by. I'll just go through some of these pictures of twilight. Keep in mind that the progression of twilight here represents the passage of days, not hours. That's the moon and Venus.
Beautiful.
When the moon and Venus lined up like this for me from the South Pole of Earth, it seemed like some kind of Stanley Kubrick moment.
Right.
Unfortunately, our actual sunrise was clouded out again, so there was no chance of the amazing green flash phenomenon that's possible from South Pole. But it was still amazing to see daylight return after 6 months of not seeing the sun at all. Many weeks later, it's become bright enough and warm enough for the first plane to return. Janet Phillips was our station manager that year, and she had the honor of guiding the first plane in. It's quite an emotional moment for us when this plane comes. Oh, the sound, the smell of the exhaust, everything about it. It's a very dramatic thing. And with this signal here, Janet's telling the pilot he's parked on a dime. He can feather his props, and symbolically, our winter over has ended. By the way, to the left of the photo, there's an American flag and a white sign down there on the horizon in the distance. That marks the geodetically surveyed location of the South Pole. A new crew comes tumbling out, and it's hugs and kisses all around as the cycle of activity at South Pole Station begins again for another year. Thank you for your attention.
Wow. That was amazing.
Awesome.
Yeah.
Completely awesome.
Yeah. So
That was amazing, John. I mean, Thank you so much for sharing that. That was just incredible.
You're very welcome, everybody. It was a little tough. I have never given the show in a compressed time frame like this, but I still think that even in just the 18 minutes or so we spent looking at those pictures, you really got a feel for what some aspects, anyway, of what life was like there. And usually, I have I exposed about 3,000 slides over the course of my time there that year, and I've taken my 80 favorite in a slide carousel, and I've shown the slides countless times, and only recently finally scanned them. But anytime I show them via computer or still with an old slide projector, I'm inclined to turn it into a movie length presentation because there are so many anecdotes to share about what it was like being there. But I tried to move along because our wonderful short subjects on these star parties, it's obviously it's the way to go. But I'm real happy that it occurred to me to dig those out to share with you all. So there.
Yeah, it was great.
It's really impressive.
John and I were talking about this hostile world of Antarctica before we put this before we started Global Star Party, and I think that it's got to be very much like going to another planet. The extremes in temperature, the precautions that you have to take. Our bodies are so susceptible to those extremes, and to go down there and to survive it and to work in it and to make it all happen has to be very much like what it might be like for the moon colonists, or and then later perhaps the Mars colonists. So it's
I'll share just a couple thoughts related to that. And of course, Scott, you're absolutely right. It is an otherworldly place. That was at the heart of the adventure of it. The people there are so profoundly isolated because it's just physically now not possible to return once it really gets cold. It's too cold for aircraft to land in the middle of the winter. So you were really stuck there for the duration. And so there are interesting psychological consequences. The best way to put it is, after a while, we all feel pretty darn burned out. And you hear about cabin fever in Alaska. You hear about what they call seasonal affect disorder. The joke, the jargon around the base. Of course, we all became intimate friends. But we just talk about, oh man, I'm toast. I'm really toast. And being toasty meant you're feeling a little burned out. So the reason I'm pointing all this out is, as frequently as sometimes people in popular culture today talk about colonizing Mars and things of that nature, sure, people can go to the moon and go to Mars and all that. But one thing I know is, if people go somewhere like Mars and try and live there for a while, there's only going to be one thing these people are going to want to do after not so long, and that is simply get back home to the wonders of Earth and the beauty of our nature right here. So sometimes the people talking about space exploration, they don't understand the practicalities, the psychological practicalities of even doing something at South Pole Station in a mere winter rover. But it was really fun learning that by firsthand experience.
Wow. That's great. John, thank you so much for all these great presentations you're bringing to Global Star Party. It's awesome. There are people here that are mentioning how great of a storyteller you are, but it's maybe not too hard to tell a great story when you've been on such a great adventure like John has.
I show a lot of pictures to try to convince people that I am not simply making it all up.
You need photographic proof. Right. Well, okay. So thank you, John. That's awesome. I look forward to more. Well, it's time to bring in Libby. Libby in the stars. She has grown not only in her abilities to give presentations, but she's actually gotten taller since I've met her. And that has, that's been less than a year. So Libby's growing up, and she's, I think it's awesome that she's surrounded by so many wonderful astronomers and so much inspiration. And she gives that back to us in her presentation. So Libby, I'm going to turn this back over to you.
Okay, so I have a presentation to share. Let's see if I can share this. Let me present. So I decided to do moon phases because I've been doing a lot of moon phase observing, and I have an amazing story to go along with this because one of my neighbors, when I was first getting into astronomy, I didn't even have my huge telescope. It was just my small telescope. And I was showing him every night like the moon. And this is my best friend's grandpa. And I was showing him the moon almost every night. And he would say, okay, I want you to observe where the moon moves across the sky in different phases. And since then, I've been on a huge hunt almost every single time I observe the moon, I think about that story because it's just so amazing. And then that's how I really got into doing a bunch of moon phase observing and a bunch of that stuff, and how Earth orbits the moon orbits our Earth. Wow, that was a tongue twister. But basically, a moon phase is when the sunlight is like hitting on the side of the moon, and we may be able to see it and we may not be able to see it. And I love the moon because it's just something that people who are amateurs and people who are like really good at astronomy, like professional astronomers, both can look at the moon. And every single time I look at the moon, I get the same wonder that I did just from the start. And I'll put my 6.4 lens into my Dobsonian telescopes, and it's every time that I put it in there, I'm always just so amazed by the power of the moon, and it's just so beautiful, and you can see all the little craters and everything. And I love the moon for that reason. Everybody's amazed, even if you're a professional astronomer, and even if you're just getting into astronomy. And so if the sunlight is hitting the moon on one side of the moon, and we may be able to see it, but it depends on how Earth's alignment is with the moon. Because if it's a new moon, then basically if it's a new moon, the moon is facing the sun, and we're seeing the side of it that's in the shadows. And this changes when the moon orbits around Earth. So I love this chart just because I think it's always a hard thing to explain, and it's a hard thing to get through, but I think charts always help. So here are all the moon phases. So the new moon means that the moon is facing the sun, and we're seeing the shadows. And this basically changes as the moon orbits around us, because then we will be able to see more of the part that is in the sun. And it just makes sense with all of these. And I think the moon is just such a wonderful thing because there's so many things that I love to observe on the moon. And I remember when I was first studying astronomy, I was always trying to find, I was very into space exploration. And I was always trying to find all the little, where the Apollo flag was. I know it'll probably be very hard to find that, but I was looking at all the craters. And I remember one time I took a picture from my class of the moon's shadow where it ends. And I told my class a little bit for like 5 minutes about the moon and how it has shadows and how it orbits around our how it orbits around Earth and how we see the different parts of the moon. And I just love to share that with my class because I think we were all amazed by it. It's my science class, and my teacher loves to have me share to my class too. And I was telling them about the moon is facing the sun, and the sun's like right here, and so Earth is right here, and the moon's moving around. So all the shadows change on the moon, and it's kind of like if you go outside. If you go outside during the morning, you'll see your shadow is like very, very long because it's sunrise, and then it gradually gets shorter over and over, and probably till about 5 or 6, which is when sunset is, and your shadow just gets longer and longer as the day progresses. So think of yourself as the moon, and think about your shadow. So another thing I love to do is, if you see over here, this is a little bit easier to see. You can see the craters of their shadows on it. I love to observe that with my telescope, and I just think the moon is something amazing to observe because whether you're a beginner or just someone who's been in astronomy for a long time, I love to observe the moon. And just the other night when I was observing with my telescope, I had my 6.4 lens in because I've been trying to train with that to do some more nebula observing with my big Dobsonian and observe the Andromeda galaxy. And I put my 6.4 lens in, and I remember the first time that I put my 6.4 lens in, and I was just blown away. I was able to see all the craters in the moon, and it's almost like you're flying over the moon. It's that close, and I could see the edge where the shadow stopped, and I would be able to see the different craters and everything. And I've been really like enjoying that too. And I remember sharing that with my friend and her grandpa next door, and they were both amazed too. So I just love sharing the moon, and I think that it's something that the world will conquer and conquer more at a time, because I know right now we are trying to get to the moon with the Artemis mission, and I believe that will set a colony on the moon soon, and Mars, because I know Artemis is a branch out to Mars. So I definitely think that'll happen soon, and we'll get to see the moon even closer in the future generations.
Yes, that's awesome. Libby, there was a question if any of those photographs were photographs taken by you.
I have a bunch of photographs of the moon. I just went observing the other night, but the camera wasn't working well with me, and those photographs weren't me. I just took them from, what NASA has and stuff like that.
Oh, yeah.
But I definitely love to share my moon photos sometime because I have a bunch from when I observe. And the other day when I was observing, I observed with my mom's. I take my photos with my mom's phone, her little iPhone, and it's way harder than you think because so the light comes in through the telescope, and then it goes into your eyepiece, and the light that shows you that goes in your eye, it's so hard to get that lined up because it's so hard to get it lined up with your camera because it just completely, like, the light around it moves, and it's just so hard to get it like put on there. And then I'll put my little adapter on there, and then the whole thing will shift completely. It's just very hard to do with a cell phone. I hope to get an astronomy camera soon and look into more of cameras, but right now I use a little cell phone and my mom's cell phone, and I remember I was on a meeting with some other astronomers for my area astronomers, and Mike Wiesner came on and he shared about some astronomy apps to take photos with.
Oh, that's cool.
So
Yeah.
I try to use some of that and do some more of that instead of having to use a camera that's meant for Earth and not space.
So Libby, do you know why it's so hard to line up the phone camera to the eyepiece? Do you know the reason?
So there's a beam of light that goes through, and you're trying to get the camera lined up with the beam of light so you get the full view of the moon. And I remember when I was observing the other day, I had my Dobsonian in my observatory tent, and the light reflected on the tent because I had it almost backed up against the tent when I was trying to get it lined up with the moon. And on the tent, it was projecting what the telescope was seeing.
That's cool.
And so I saw it on the tent, and there's a beam of light that goes through to the top piece that's like this, and then goes through the eyepiece, and you're trying to get your camera completely lined up with it. And it's very hard to do, but I hope to upgrade soon to something that's a little bit easier to take it with. I know there's a bunch of eyepieces out there that get rid of light pollution, because I live in the town that Walmart was created. So we have a bunch of Walmart trucks coming in, like when I'm observing at 12 a.m., when I'm out there observing with my telescopes, and the light pollution. And it's always so crazy.
You know,
So the reason,
one of the things you can try is holding up a white card, okay, and let the moon project onto the card and then photograph the card. You can do that with your iPhone. And
That's an easier thing to do.
Yeah, that would be a little bit easier than trying to get it over like a pencil wide piece of beam of light, you know, so.
Because the iPhone is used to seeing what you see on Earth, but they don't really get the concept that I'm trying to take pictures of space right now, and I don't want to take pictures of Earth and what the camera sees, the basic iPhone Apple camera. I want to upgrade to what
Real Astro
what a
camera.
person sees with their eyes.
but you know what it is, Libby?
Yeah, well,
It's called that beam of light is called the exit pupil. And you think about the pupil in your eye, right? It's quite large compared to if you look at if you flip your iPhone around and you look at the size of that camera, the actual camera lens is very tiny, right? So that's the reason it's so hard to get that small pupil, if you will, that's on your camera, on your phone camera, lined up with the beam of the because your eye is more adapted for an eyepiece, right? Which has a wide exit pupil. And that's why if you use a astronomy camera, they have a big sensor, right? So they get the whole beam of light. That's the reason why it's so much easier to use an astronomy camera compared to a smartphone.
An astronomy camera has a camera that's good enough to take in the beam of light, because I know those are actually made for space and not the basic iPhone.
Or DSLR, yep.
Yeah, that's the way I do it.
Or
I take DSLR, my big wildlife lens, and I point it right at the moon. Of course, I'm not doing it tonight because it's completely clouded out where I was. But yeah, it is one way to get it. There are a few different ways. Astro camera and telescope, you can do mosaics and get really good detail, like you do. Your image of the moon that you had was fantastic. I think the last star party. So there are plenty of ways to get it, and all of them are good.
Thank you. I probably spent about 30 minutes trying to get the camera lined up with the telescope, and I think I'm soon going to advance all my telescope stuff once the world opens back up again, because I know I'll be doing a lot more astronomy once the world opens back up again. I always tell my mom, if I ever get frustrated when I'm trying to get it all lined up, I always just drop the phone on my chair, and then I say, you know what, tonight I'm just going to observe with my eyes. And I'm like, that's it.
Good idea.
Don't ever forget that, because that's This is a perfect way to do it. The moon tends to come back. We typically see the moon with our eyes as full, even though it really isn't. And this is day 2 where it's as full as it's going to be, and then it actually becomes a really big waning gibbous. But you get 3 days to see a full moon generally, and then each successive day you're seeing a waxing or waning, a waning crescent until it gets closer and closer to the sun. And then the cycle starts over next month. So if you miss one night, try again the next night, and rest assured it'll come back.
Yeah.
That's a lot better than throwing your iPhone, your camera, and everything else into the lake, because it's hard to retrieve it, and a lot of times it won't work after that. So yeah, anger's not a good thing to have when you're dealing with anything with the night sky.
A month ago, I went to Mount Magazine, which is the tallest point in my state, and we went on a huge road trip up there with my Tasco telescope, and I put that on top of the roof, and I just sat on top of the roof of the car because I actually got really scared because of the bears out there. There were bear signs all over, so I wasn't sure if I was going to make it once I got out there, and it was really dark. So I had the telescope on top of the car observing, and I told my mom that night, I was like, I don't want to take any pictures of the moon because this is my first time really looking and observing for more than an hour with my Tasco telescope. And I ended up since I wasn't so stressed, I ended up being able to see Neptune, and I got to see the moon too again. And I saw Neptune, I was like, oh my gosh, it's beautiful. I can see like all the different blue shades and colors, and it was just so nice not to be stressed trying to take a photo.
Yes. That's also something to consider when you see your first total eclipse of the sun. You know, a lot of people get really stressed and anxious over that whole process of taking pictures of this total eclipse, and they miss the beauty and grandeur and the life-changing effect of actually just watching it, you know. So if there's a way to do both, that's the best combination. But in order to do both, you have to practice a lot, and you got to be really prepared, because it just happens in a few minutes, or sometimes just a few seconds, and then you got to wait for the next one and chase it somewhere else on our planet Earth.
I mean,
Libby,
you can
thank
either
you.
think I'm going to get a photo of this, or you can either think this is life changing. I'm seeing the sun right now with my eyes.
Yeah. I think it's worth doing both. That's great. Libby, thank you. Thank you very much. Up next is Chuck Allen, Vice President of the Astronomical League, and he is doing, the Astronomical League is our door prize sponsor. They come up with the questions and do with random selection the winners, and they do an amazing job. They've been incredible supporters of the Global Star Party, and I have been remiss in counting how many times you guys have been on, but it's been a lot of times. So, and Chuck Allen is someone that's also, aside from just doing the Astronomical League's door prize portion, he's giving amazing presentations of his own, and I think that's going to happen again tonight. Chuck, I'll turn it over to you. Thanks for, we've been going long tonight, but that's okay. It's been really an interesting night, and but I'll turn it over to you for the door prizes.
Great, thank you. And I think you've got it backwards. Scott, you have been the great supporter of the league throughout all of these GSBs, and we greatly appreciate it, as you know. And John, I'd like to add one comment to you. I spent a year in Alaska, northern Alaska, in the Air Force back in the 1970s. So I know a good, what you said about being toasted resonates rather well. the long winter and the short nights. Of course, we did have 2-hour days during the middle of winter at our latitude, but I understand where you were coming from on that, and I really enjoyed your program.
Thank you very much.
Yeah. Okay, so we will go now to, let's see here. Hold on just one moment, please. Okay. We always start with a warning because some of the door prizes may involve items that you could use to observe the sun. And we'd like to warn everyone, especially people who are new to astronomy, to be very careful about observing the sun because you can be blinded by observing the sun through optical equipment without proper filtration, far faster than your brain can react to the fact that you're seeing light that's far too bright. Never observe the sun without professionally made solar filters that include energy rejection filters securely mounted at the top front end of the telescope. Don't use makeshift filters or solar filters that attach only to the eyepiece. Never leave a telescope or binoculars unattended in daytime, especially if children are present. They will occasionally try to use them to observe the sun, especially if you're conducting solar observation. Be careful of solar eclipse glasses. They are intended only for use with the naked eye, that is looking straight through the eclipse glasses at the sun, not for use with binoculars or telescopes. And they should be certified according to international safety standards. It's best to buy them from reputable sources so you don't end up with some counterfeit knockoff that claims to be certified. Always cap your finder scope so you don't get burned in the cheek as you're observing the sun through a properly filtered telescope. And contact somebody at a local astronomy society, find someone there who knows how to observe the sun safely, and they'll help you get into the process. These are the answers from GSP 42 held a week ago. And the first question that President Carol Orge asked was, what is the name of the bright red star here in the constellation of Scorpius? And the answer is Antares. The second question is, what is the name of the United States Mars rover that arrived in February of 2021? Perseverance, of course, much in the news today. Question 3, what star appears at the end of the handle in the Little Dipper? And the answer to that, of course, is Polaris, pointed to by the end stars in the bowl of the Big Dipper. The following individuals correctly answered these questions, and their names were added to the door prize list. And we use a random number generator and award door prizes on the last GSP of each month, and that would be tonight. And I'll announce this month's winners in a moment. First of all, though, the questions for tonight, this is GSP 43, and remember to send your answers directly to Terry Mann at secretary@astroleague.org. Okay, the first question. This galaxy in Virgo is named after a type of hat. What hat is it? Okay, question number 2. Proxima Centauri, the closest star to the sun. What kind of star is it? Is it a red dwarf, a brown dwarf, a red giant, a blue supergiant, or a sun-like yellow star? Multiple choice. And the final question, a well-known star-finding rhyme tells you to use the Big Dipper's handle to arc to Arcturus and then speed on to what other bright star? Okay, that concludes the questions for tonight. And now to the winners who were selected for this past month of April. And they are Book Davies, Matthew Walsh, and Andrew Corkill. Congratulations to you, and Carol Orge, our president, will be in contact with you shortly. And that concludes for tonight. But I would like to add one thing, Scott, if I may. We are in the process of preparing for Astronomical League Live 6 on May 7th of 2021. Again, this is a league event that you're welcome to join, and it's also hosted by Scott, who very generously takes his time to assist us in presenting these programs. Also, be looking out for information about our upcoming virtual convention on August 19th through 21st of this year. This will be Alcon 21 virtual. It will be 3 afternoons and evenings of speakers, virtual tours, a slew presentation, awards to both our youth awards and adult award, general awards for 2020 and 21, and door prizes, really nice ones that are being sponsored by our member societies, will be given to people who register for this convention, and the registration is free. That will be done on our website, which will go up in mid-May, and be looking for more news about that. And with that, I'll turn it back to you, Scott.
Thank you very much. Thank you very much. Well, it's always fun to have our door prize section here. I know that some of the questions, sometimes they're a little tough, but sometimes they're relatively easy. But you know, the league is there to get your brain going, you know, and to keep you focused on astronomy. Our next speaker is Pekka Hautala from Sweden. Pekka has joined us on several different global star parties, and he's recently been fighting and winning the fight against light pollution, and so he's going to give us a little bit of an update. And after that, we'll take about a 10-minute break and come back with Jerry Hubbell, who will show us some astrophotography. So, Pekka, I'm going to turn it over to you.
Thank you, Scotty. Can you hear me?
Yep.
Good.
Like your T-shirt. The NASA shirt is good.
Thanks. Okay. So 2-3 weeks ago, I got stuck by a photon wasp. I got a very high light pollution fever, and it's just rising. And for 1 week ago, I was sending 2 emails, one for the Green Party, the headquarters, and one for the local politician. And I got the call back from her, and she knew a little bit about the light pollution. And she knew that she had seen a motion and proposal for the Parliament of Sweden, and she promised to find it out, and she found it and sent it to me, and I read it and saw that name who had written that motion and proposal for Swedish Parliament, and got contact with her, and she was extremely interesting about my story about amateur astronomers and the light pollution we are fighting for. And she wanted to talk to me. She would call me today, but maybe tomorrow, otherwise I will call her. But I have one document that I have Google translated for you to view, and you can read it. This is really good news for us, that our government has thinking about it. Say if I have to make it more bigger, so I can scroll it down when you have read it. This is from the left party, we can say. It's like Republicans. I don't know, we don't talk politician here, but this is one of the biggest parties in Sweden, and one of them have written this proposal. Just scroll down a little bit, so. It's just one A page, A4 page, and you don't use that format in US. You use letter format, I think. can I scroll down?
Yes.
Awesome.
And my target is to ask her what has happened after this has been written, 2019 August, and what has been which decision has been made, if the light designer has been employed, and if not, what is stopping it. And I will be hard. I have written down all arguments they can possibly make to me. It's included everything. It's included all the medical cost and treatment for people's melatonin disturbance and so on. I have written down everything I can possibly think. So if you have something, mail me, please. Scotty has the email address.
Yes.
Or I can post it here. If you have some kind of questions or arguments, they can come to me against this. What I have been told them that we think they should do. So it's welcome. So I have the answer to them immediately.
Pekka, have you checked out the International Dark Sky Association website?
Yes, I am a member of it.
Okay,
them.
perfect.
Yes, and I am an advocate also.
So Scott and audience and Pekka, I mean,
Excuse me, Cameron, I didn't hear.
Well, I was just saying, I'd be happy to volunteer to read it out loud if no one objects.
If you want to read this.
Yeah.
From beginning.
Yeah.
Go ahead.
Yeah. So City Council Motion 2019, motion by Sarah Stenud.
Yes.
The city should hire a city lighting designer to promote biodiversity. So-called light pollution is a problem that has been discussed for many years, but which with continued urbanization has become increasingly acute. From the beginning, it was mainly astronomers who used the term then to illuminated cities, got a kind of artifact lid, SC sky glow, which meant
so-called
that
sky glow.
So-called sky glow, which meant that you do not can see the moon and
that's
the stars.
A little bit.
For us,
that's a little bit.
That's okay.
Yeah,
for us
this
humans,
is Google translated.
No problem. For us humans, it is sad but not vital to be able to see Milky Way a starry night. But for nocturnal animals and insects, which largely navigating for the stars, it is vital. The world is facing a mass extinction of insects, and scientists fear that as much as 25% have already disappeared. The insects disappear like that if the pollutants disappear, and then they disappear. We will not get any more food. Their survival is absolutely crucial to us humans. This mass extinction has several causes, but an important factor is the light. And it is also something that the city of Stockholm can influence. Can you scroll up? Yeah. To solve this problem, the city should adopt one lighting strategy and a lighting designer in the same way as we have strategies today for other environmental challenges and both urban architect and city gardener. This lighting designer would be used at an early stage of the planning processes to provide lighting that increases security and aesthetic values, but also take into account environmental aspects, energy saving, etc. With reference to the above, I claim 1, that the city commission the relevant administrator prepare one lighting strategy, and 2, the city creates and appoints a position as a lighting designer. Stockholm. Very good, Pekka. This is well done. Well done.
Thank you. So let's see. I have to stop sharing somewhere. But where? Where am I?
Yeah, I can help you with that.
Can you, Scott?
Yep.
Thank you.
There you go.
Thanks. Thank you. So that's my task, to follow up that document, what has been done, what should be done, and so on. And that's all for me today.
It would be amazing if Sweden became the first dark sky country, you know.
Yes, and that's my target, to begin with my balcony, and that's ongoing. I had a visit from an electrician and technical advisor for my landlord, and he told me that there is no problem. He will send a guy who will attach some plates and turn around some lights 10 degrees down, and from the parking place a little bit off 10 degrees. And I told that, okay, that's nice. So it's ongoing. Those bugs, you told me that those high streetlight was.
Yes, that's great.
They will be down very soon.
Yes.
Pekka, your fishing rod, you had your fishing rod tent, right? You had a fishing rod tent.
I will return that to the store. I have the receipt, you know. I have that left, so I can leave it back and collect my money.
That's super. That's great.
But my light pollution tube filter is for sale. So if somebody needs, I will send it to you. Yes,
right.
Anytime. Or the museum for light, city lights we had before. So this is the antique equipment astronomers used those days. We had very much light pollution. So I will start a light museum someday and show pictures how it
used to be.
How it used to be. Yes.
Mm-hmm. Very interesting.
Thank you, Scotty.
Thank you very much, Pekka.
Okay.
Thank you.
Thank you.
All right.
Bye-bye.
Okay. All right. Good night, Pekka. We're going to take about.
I will stay up and join the after party.
Okay. All right.
You know, my melatonin has dropped down so much because I have those LED lights up there.
Oh, I see.
Yeah.
All right. We're going to take a 10-minute break, folks. So get up, stretch your legs, make a sandwich, have a cup of coffee, and relax for a few minutes, and we'll be back in 10.
Hey, Scott.
Yeah.
I want to test this out again. So can I?
What is this? You're sharing again? We can do that.
Yeah.
Okay, let me stop sharing.
Cameron, thank you for reading up that letter.
Oh, my pleasure, Pekka.
Okay, thank you.
Thanks.
Hi, Adrian.
Hey, I am coming to you live from a failed mission to capture Moonrise. Fortunately, I have some other pictures where I was successful.
I was just looking for 10 minutes ago a moon set.
Yeah, so I think we're on opposite sides of the globe.
Yes.
The moon did come up, but it came up behind a lot of clouds.
Yeah, I think that it was setting for me.
Yeah. So
it's amazing.
So I was unsuccessful. I had everything. I had the flashlight right here. My camera's still attached to the tripod, and I just threw the whole thing in the back seat. But yeah, this is my we do it for real sort of. Have the light showing right there, and I do have a couple pictures where I've attempted Moonrise, but I haven't gotten quite the perfect Moonrise yet. I've got a couple pretty good pictures, but I'm still in search of a beautiful yet detailed Moonrise, and I've tried a couple of different settings.
But you had a
I stumbled
sunset.
upon one.
You have a sunset right now.
Yeah,
because we have a sunrise right now.
A couple hours ago.
We have a sunrise right now.
Our sunset was at 11. 3 hours ago, Eastern Standard Time, it set. And stars were coming out, but then clouds came out. And I do have some interesting pictures, but it's clouds lit by the moon is all that I was able to get.
But
So
isn't it
it was,
a little bit strange to, we are talking right now, and your sun is set and mine is rising.
well, I love it.
Yeah, me too. Me too.
Well,
It's like,
speed
it's
of
like,
light kind of helps with that.
Round.
yeah,
Well,
is it? Are you sure, Molly?
yeah, the Earth is
It's not just
round.
reflecting
Yeah,
somehow.
it's the same. Well, no, those that are flat earthers, for them the Earth looks flat because their view is very narrow. So all they can see is flat. So it's nothing to argue about.
No.
We see and know about the Earth as being round. We're able to think beyond ourselves. And to me, that's very important. I mean, we don't just know our various areas of astronomy, astrophotography, we share it. And, you know, we're not out for conspiracy theories. So we observe.
Yeah, I
Right on,
actually
Adrian.
saw.
We're not afraid of the unknown.
You know, I saw a documentary about the Flat Earth conspiration team or group in States, and there are 2% of the population in USA that still believes. Is that true?
I think there's I think there is a small percentage.
No.
Yeah, there's a percentage that believes, and I know I'm probably yelling here, I'm sorry. There's a percentage of folks that do really believe the Earth is flat.
Yeah.
A lot of the flat earthers are in love with conspiracy and, you know, just don't trust any authoritative figure.
Yeah, they did a test for them.
They'll say the Earth is flat to be contrary, but you know, it's more of they just hate authority. Whereas there are people that
Adrian,
truly.
Have you seen that documentary about them? They collect them, many of them, on the beach, and they have a boat with a sail with stripes, horizontal stripes, and they put that boat to the horizon, and because the Earth is round, so the sail was disappearing behind the horizon. And they asked that, are you still believe? Because the boat was sinking below the horizon. They asked if this is the proof that the Earth is round. No. That's just optical diffusion about the the vibration of the atmosphere.
Use as many big words as you can. Optical diffraction.
Yeah.
Total luminescence of the biosphere. Anything. Yeah, it's science that is proven has been presented to peers. It's been tested with independent study. It's been tested again and again. If someone comes along and gives us an incredible proof that Einstein's theory of relativity is missing something or is in fact wrong, the evidence better be very solid because the theory of relativity has stood the test of time. However, time itself, we know, can go millions of years. And in those millions of years, there's no telling what we will learn should we still be a species on the Earth. So it's all about being willing. And I'm someone who will say, yeah, glory to God, I go to church and still appreciate and follow science and try to use the scientific method for solving problems. It isn't just you're for science or you're against it. You understand what the scientific method is about, and you trust the results that have been handed down over the years that we've been around. And if you have no real way to disprove it, you accept all the theories that are out there. So yeah, those are my thoughts on it. It's tough to argue. You know,
Yeah.
when it comes down to
whole different
you know.
question to everybody. What difference is with star test and collimation?
Yes.
Start, go for that. I think Cameron, you probably got this one.
What's that?
Yeah. So star test is actually a method of collimation. Is that it can be
Is
used
star
for
testing a
collimation?
method of collimation?
No. What's the difference? What's the difference between the two? So
Between
collimation.
star testing and collimation? Well, collimation is the alignment of your optics, you know, for getting everything effectively zeroed out, where if you have a refractor, you have all the optics in perfect alignment. So when you have a star, stars are going to perform at their best. They're going to provide the tightest airy disk. If they're tilted, then it makes the stars distorted and angular, and it's hard to get a good focus. You really can't get a complete focus from edge to edge, with a or over its optimal field, theoretical optimal field, unless the optics are collimated. Star testing is the ability to take is where you take a collimated set of optics, and you can throw the image inside and outside focus and look at the diffraction pattern. You can look at the rings. You can tell if the telescope has spherical aberrations, astigmatism, turn down edge, those kinds of effects. So you're able to determine the optical figure to a large degree, and some amateur astronomers are really good at it. They can throw a star inside and outside focus and tell you pretty close what the wavefront of that optical set is. So that would be the most experienced of the star testing guys that I've met.
I love how Scott, you just jumped right in. This is your passion. I love it. This is awesome.
Scott, that has nothing to do with the optical test of first take a picture of the star in the middle of the frame, and then on each corner of the optics.
Well, when you are doing, astrophotographers, I mean, the holy grail for astrophotographers is to have perfect stars from center to edge, and so with a lot of telescopes, most telescopes, it's going to require some sort of corrective optics in order to do that. Because you've got, Schmidt-Cassegrain telescope, you've got a curved focus, okay? So you need a field flattener there. A lot of refractors, you need field flatteners. There are, and so it is this curved focus that is the demon for most astrophotographers. And so they'll take a shot in the center, and then they'll look at this edge, this edge, looking at all the stars on the edges, and do pixel peeping, as it's called, where they're blowing up the stars, 400 or 800 times and seeing just how good they really are. Okay.
Yeah.
And
okay.
So that's
because I saw a program or stream today from a Finnish Astronomical Society, and there was a guy that had a 500 millimeters skywatcher. It was an Dobsonian, and when he was doing his star test, and in the picture, he showed us behind the mirror there is those where the mirror is fastened.
Oh, right. So the mirror support structure itself is coming
and
through
you
the
could
glass.
see those through on the picture.
Yes.
And there was on the manufacturing of the mirror, they had done something wrong.
No,
Because-
that's not necessarily true. That
Okay.
mirror could be fine, but it's now held in this metal cell. Okay.
Yes, yes.
So when
and
they
you could
assemble,
see those
yeah, and you could
on the picture.
You can. All right. So someone that is concerned with that kind of thing would just take the telescope apart, okay, pull the mirror out of that cell, rest it back into the mirror cell itself so that nothing's really squeezing down or pushing against it very hard. Okay. The idea is you just want to have it held in place so it's cushioned.
Floating, like
Yeah,
floating.
so you might use like cork or pieces of felt or something like that to kind of just make that snug. But if you start to nail that thing down, you will see that the mirror cell itself will start to translate right through the glass, because the glass, it's not really a solid. It's somewhere in between a solid and a liquid, and but if you relax that mirror, you'll find that the thing will work out very well. A lot of the amateur astronomers also never let their scopes cool down to the night sky. Okay, they get the scope out and they want to start taking images immediately. Well, the glass itself could slightly expand, or the cell that's holding it could be contracted or slightly expanding, which can cause these kinds of things to show up.
Because
So-
I'm really confused about the star test and collimation. That I can that because I have two CSTs.
Yes.
But the star test, because I was forced to release my my corrector plate from my 11-inch because the secondary was loose.
Mm-hmm.
It was rotating, so I was forced to take out the whole corrector plate.
Okay.
And I marked it first before I took it out, and then I speak with somebody here in Sweden, and he was telling that you have to do a really good star test to that scope after I have to get out the corrector plate. And I don't know what star test is for.
There are books on it. And you can probably see a lot online about star testing.
I have found nothing.
You have found
nada.
All right. Well, there are some excellent books on star testing that go from probably the 1950s or 1960s on how to test your optics and
if I just know
mostly what you're looking for, you'll put a star dead center after you do a careful collimation, okay? And start to bring the star down, down small, okay? It's still out of focus, but small.
Yes.
And then you want to push it through focus and look at how similar or dissimilar that this
the
light
refraction
looks.
around the donut.
Not only how round it is, because this would be collimation.
But I mean, in collimation, you have these round circles like earrings on three.
In your Schmidt-Cassegrain you do. Yes.
And those has to be exactly. And when you push it in focus and out focus, you can see when it's. But okay, that's collimation.
That's collimation.
What is star testing?
If you find that it looks nice and round as you're going in, and that shadow of your secondary now moves as you go through the other part of focus, that means that the primary mirror writing in your Schmidt-Cassegrain, as it's going on the slider, as it's called, but the slider is not really perpendicular. Okay.
Yeah.
And so this is something that Schmidt-Cassegrain manufacturers have fought a lot, in getting the right mechanics going, and so it's. But there's lots of issues to consider in optical design, especially compound telescopes like Schmidt-Cassegrains. They're wonderful instruments, extremely versatile, very compact, large aperture, lots of good things. Making them perfect is tough.
When they are collimated and star tested. Okay, just one quick question.
Okay.
The storage of the CST, upside down or in horizontal?
I would say if you're really, really concerned about how the grease on the slider is the film of grease, okay?
Yes.
If you want to keep that more or less concentric, if you want to store it upside down,
Yeah.
okay? Like
Like
that.
I have
Yeah, but if it's really, I have worked with people to have them re-grease their sliders and put the scope back in or the optics back in, the primary mirror, I mean, where you actually disconnect the primary from the
Yes.
focuser and all that. You can, if you find that you see some bumpiness as you're focusing, what you can do is just run the focus all the way in and out, in and out, in and out until
Okay.
it starts to smooth out again. Okay.
Okay.
All right.
Good. We could talk about this
All right.
hours. But thank you, Scott.
All right. We're holding up Jerry now. Jerry, are you with us?
Yeah, I'm here. Can you see
Okay.
me? Can you hear me?
Yep. I see you. The mission control there.
Yeah. So
How do you feel? How's
Feel
your?
good. I feel
you
all
still
right.
Feel good. Okay.
Yeah.
Your arm tender or not?
I can start to feel it now when I push on it a little bit. I can feel a little bit of pain,
Okay.
but by itself, it's not painful.
Oh, that's good. That's real
Yeah.
good. Okay.
I was told it would feel like somebody punched you in the arm,
That's what it felt like to me. So
but I don't feel it that way yet.
good.
So there was a couple things. So I got a real quick story about the MSRO Observatory tonight. I was going to go ahead and use it on Station 1. But Myron told me today when I talked to him earlier that we have a small nest of 4 birds in the observatory.
What?
In the dome. So he powered it down.
Okay.
And now I'd used it last probably a week and a half ago or something like that. So he was going to move the bird nest out and with the birds and all, but he didn't do that today. So anyway, I've got it up and running. I'm going to show the interface, the desktop, and show you a couple of pictures. And I'm also going to talk about chapter in my book, my first book, Scientific Astrophotography, chapter 8, which is about environmental effects and how it affects your equipment and yourself when you're doing your observing. And I'm going to focus on things to keep in mind when you're observing out late at night, especially in extreme weather, somewhat extreme weather, which kind of goes along with the theme earlier that we had with the talk. So let me share my desktop first, and I'll share the observatory. Where's it at? All right, do you see that? That's the desktop of the observatory.
Yes. Mm-hmm.
All right, so I just wanted to show a couple of images. This was an image that actually the session I had with Pekka. This is NGC 2264.
Mm-hmm.
Which turned out this is a 3-minute exposure. All right, but it's cool that you can see these dark lanes here just after 3 minutes.
Oh yeah.
And this is the
Nice.
This is a wide. This is the system's got the 6.5-inch refractor, and it's got a focal length of 851 millimeters. So it's a wide, fairly wide field view. It's a 1.3 by 0.9 degree field of view. So that gives you some idea of what we're looking at here. It's basically you could fit 4 moons in here, pretty much.
Huge field.
So that's kind of cool. And then I took last month. I used M67 to do some calibration of our filters, the V-band filter, because there's a lot of the AVSO has reference photometric stars in this field that I use, and I also use the UCAT catalog to create a relationship graph between the catalog V-band magnitude and the measured magnitude, instrument magnitude that's on here. So I can do basically do a linear fit and calculate the filter to the V-band reference basically in the catalog. So these are some images of M67 that I get with the scope, just to give you an idea of the quality that we have on this system. This is taken with so we got kind of an odd configuration that most people wouldn't consider probably. We've got QHY 163 one-shot color camera with a filter wheel on it, and you're saying, what the heck? Why would you do that? Why not use a monochrome camera? Because we want the best of both worlds, right? That's what we want. We want all in one instrument what we can do. So that's another reason I do this V-band calibration with the one-shot color, because we're combining the pixels into the 4 Bayer pixels into 1 pixel. It's a bin by 2, and it comes out very well. I mean, it's very linear. So I've proven to myself that it's a good practice to use a one-shot color as a V-band filter. Now, you're not going to get as much light, of course, as you would with monochrome, because a Bayer pattern filter array filters a lot of the light, so it's not quite as sensitive. But this camera is in the monochrome version is a high, it's a back illuminated camera, so it's kind of like using an older camera in a monochrome mode, probably a camera that's like 5 or 10 years old. But again, it's good enough in terms of that and types of work that we're doing with the filter wheel. So I just wanted to show that what we're doing there. And so let me stop my share and select the other thing. And I've just got some talking points that I want to talk about in the book. I'm going to show. So this is the cover of my book, and then I'm going to go to chapter 8, and which is on page 131. All right, so this chapter is about environmental and external factors that impact your imaging, and this covers not just the weather conditions and things. And there's this chapter is one of my favorite chapters in the book, actually, because it's got such a wide variety of information. And it talks about what are the best weather conditions for deep sky imaging, you know, for lunar, solar, and planetary imaging. There's different things to keep in mind. And I talk about some sources of weather data. And one of the major ones that we use here in the United States is the clear sky chart that Attila Denko creates, and that's a great resource. And that's derived from weather data from the Canadian Meteorological Center. And that's what that second graphic shows. Let me zoom up on this a little bit so you can see that better. So he takes data from the Canadian Meteorological Center and basically distills it down into this chart, which is a great resource. So that's something for beginners if they want to start looking at their weather conditions and understanding how that impacts their imaging. Then this is a great source in the United States. There's also some other ones in other parts of the world. I'm not sure if I have them listed. There's one called skippysky.com. I don't know if you've heard of that in Europe.
Skippy Sky?
Skippysky.com.au. It's Europe and Australia. It's kind of cool.
Okay. Yeah, that's cool.
I don't know if it's still in service or not. I wrote this book about 9 years ago now. So that's a tip if you want to check on that. Anybody out there? So I talk about impacts to the equipment. That's me out at 2:30 in the morning at about minus 6 degrees Celsius, 21 degrees. And just sitting there for hours on end. You have to walk around. You have to get up and keep yourself warm. Otherwise it's not good. So the main thing I wanted to talk about is this section here, 8.5, the dedicated astronomer, knowing when to call it quits for the evening. So when I first started astrophotography after getting into it, when the technology came along 12 years ago, I jumped in it with both feet, and I was really passionate about getting out there every clear night. And so you get excited, you get the passion to do this stuff, and you don't know when to quit. Okay. That's something to consider. Because you're in this for the long haul, you know. Everybody gets impatient, and that's the biggest thing that astronomy ever taught me was patience. Just especially with the weather. You know, the weather is what drives you nuts. You think every time there's a bad weather day, it's a lost opportunity, but it's kind of a blessing in disguise, because it does teach you something. It teaches you that there's time to do other things with your astronomy gear, not just take it outside and try to use it. Because when you're a beginner, you typically don't understand how important it is to do, 10 hours of work inside for every hour that you're out in the field, to get your equipment working right, so you don't waste any of the time that you're out in the field. And at this time, the first 4 years, I was taking my system up and down. I was building it and breaking it down every time I took it out every night. And that really works on you. So one of the things that can get you hung up and get you frustrated is if things don't work right. All right. Right. And you get so frustrated, but you want to fix it, right? You want to sit there and solve the problem. And if you're into this for about 6 months and you think you know pretty much everything you need to know, that's when you discover that you don't know everything. And you'll beat yourself in the head. You'll spend 2 or 3 hours trying to find a problem, right? And trying to fix it. And you got to know when to quit, basically, right?
Yeah, it's like a lot of skilled lifestyles or hobbies. Like I used to be into scale modeling as a teenager, okay? And so we would build ships and very intricate things. Like one of my friends was into building P-51 Mustangs, and he would make the instrument panel and working controls inside and seat belts that worked. And I mean, everything, all the way down to the rivets on the airplane, had to be authentic. And he was extremely skilled in making, scale model things. But one of the things he taught me was, he said, you just need to know when to stop and walk away. He said, because you keep going, you'll mess it up, and
that's right.
And that's true in astronomy as well,
And you
can go down that rabbit hole and tell yourself, and I've had many people tell me, Scott, I'm an engineer, Scott, I'm a doctor, Scott, I'm a lawyer, Scott, I'm a scientist, I should be able to understand this, okay? And they will. It just takes. They will,
right?
It just has to happen for them.
It's a different animal from a lot of different stuff.
Enjoy the journey. Enjoy the journey.
Enjoy the journey.
That's right, Cameron. That's what the hobby's about, right? It's the journey.
That's right. That's right. You're on an exploration of the universe, and your gear is part of it. So mastering the gears.
I learned the hard way that I started planning. If my gear doesn't work tonight, I'll go manual. I'll just look up. I'll at least make sure that I'm not leaving a park with a beautiful sky up here. I'm not leaving upset because of my equipment.
Right.
That's right.
What I have learned is that when you have a good image, don't touch anything. Don't do anything.
Nothing.
The perfect is
got
the
it all
enemy
dialed
of
in. That's right. Yes.
So
and it's kind of a sorry.
Go ahead, Ken.
Oh no, I was just going to say it's that balance between quality and quantity. I mean, when you're first doing something, you want to do as much and absorb it all and just drink it all in, right? and then you're just trying to do all the check boxes, and then later on you want to kind of enjoy it like a fine wine or whatever. It's like you don't want to guzzle it down. You want to just try, for example, a little scope. I love little scopes. I used to have an 18-inch Dob, and I'm just loving to just seeing and seeing what I can see with a small telescope. Familiar objects, and it's just so enjoyable.
Well, that's right. And so one of the things you'll find that I've found over the years is that, you talk about world class. What does world class really mean? It means getting your skills and knowledge to the peak, right? Where you can use any instrument and you'll push it to its very limit. You know more than the equipment, basically. You know how to use the equipment so well. That's what a world class, to me, a world class observer and imager does. They push the limits of the equipment to the max.
Right. Musicians do that with their instruments, and they go from making sound with them to playing them,
Right. So you may not have as good equipment as the next guy. His images looks a lot better than yours, but the limit is the equipment. It's not your skills. That's the thing, Well,
yeah, like I took a $200 telescope and I put a $400 eyepiece in it, and it is amazing. It's fantastic.
That's right.
That's
right.
It does it wonderful.
Yeah. It becomes
and you put it on a $500 mount, and then it's even better.
Right. So one of the other things that you can run into as a somewhat a new observer is that you'll start out you're basically just playing around at some point. You're basically going from one object to another. You're not doing it. What I'm saying is you're not doing any planning ahead of time on what your goals are for that session. You don't have any real goals in mind. You just have, I want to try to find this tonight, or I want to just search around this area of the sky and look and see what's there, that type of thing. But as you go along, you'll start planning your observations. You want to make the best use of your time under the sky, especially when you're into astrophotography. That's when you really start planning and understanding and making sure your equipment works well before you take it out. And then at that point, then you'll have a specific configuration set up for your imaging, and you'll start to try. You'll revert back to your old days when you're just a beginner, and you say, "Well, I want to try this," and you'll start taking your stuff apart in the field. That's a bad thing. You'll frustrate the hell. You'll frustrate yourself, right? You'll say, "Well, I'll just make this change, and I'll be able to do this or that, whatever you're trying to do."
Don't do it. 'Tis folly.
Yeah, it is, exactly. And that's right. And then you have to step back and say, no, I can't do that. You'll learn that a couple times. When you try to do that, you'll learn that there's a time for everything.
And that same goes with buying your gear, right? I mean, you want to get the most use. The best telescope is the one you use, right?
Right. That's a big piece, right?
So you like you said, Jerry, I mean, we just keep on, you start learning all the capabilities of that, and then you say, oh, I need to add this, and then you add that instead of buying it all at once. I mean, it's nice and you get excited, but with experience, it's really nice to be able to just gradually add and really tune the capabilities of
everything. And then you'll know when to replace something too. You'll say, well, I pushed the limits of this scope. I need something that's better.
Yes.
And you'll be able to recognize that.
Yeah, few people actually have pushed their equipment to its limits though. And you see that with people who have done who've gone past what a lot of people would think are the boundaries, Telescope manufacturers are famous for putting up numbers like magnitude limits and those kinds of things on telescopes. I have visually seen 15.5 magnitude stars through an 8-inch Schmidt Cassegrain before. Okay, you have to learn how to observe. We have people that are amazing astrophotographers. One of the guys that stuns me again and again currently is Jason Gunzel. He's known as the vast reaches. He uses an achromat, not an apochromat, okay, an achromat that was not really designed to be an astrograph. And he makes mind-blowing images with his achromat, and narrowband filters. So recently he's upgraded his focuser he put a precision moonlight on there, and it's just given him that little bit more sharpness, because everything's held a little bit steadier and all the rest of it. So it's amazing to see that. And so, it is, a lot of times it is about, once astronomers think that they have reached the limits of what it is, they should take another deep dive back into the basics and push as hard as they can to see if they can go a little bit further, and and if they do that, a lot of times they're surprised. Hey, wow, I did capture this data, or I did see this, so.
Well, and then the other thing is that once you've got the skills and knowledge developed on the system, now you have really good knowledge of that equipment, right? So now you can start inventing techniques to do different things.
Right.
In addition to the hardware, you can take, there's also the software side of it. You can take a set of data and process it early on in your travels, and it'll look, okay or terrible, and then reprocess
or
it.
Terrible.
Get a whole new thing out of it. Like I recently reprocessed some one of my first narrow Hubbell palette narrowband images I took like 2 or 3 years ago.
Awesome.
The first process I really didn't like at all, but using new techniques in PixInsight that I learned on the Astro Imaging channel, I was able to make a really stunning image out of a single night's worth of narrowband data.
Oh, wow. That's great.
And yeah, so you can
Really
go back and
encouraging.
reprocess old data that you thought was bad, or you just didn't have the skill to do well with it, and then get something awesome out of it later on when your processing skill is better.
Right.
Yes.
Yep.
Astronomy is all about appreciation. It's really about appreciation of nature, of limitations, what you have, right? The stuff that we have, the capabilities in our, in quotes, primitive telescopes that we have are just amazing compared to what they had in the past. So just that appreciation and that knowledge growth and respect for what the limitations of everything is.
So one of the last things I have as a tip is another thing occurs when you're having a great session and you don't want it to end. Okay. You're just having such a great time. You've been out there for 6 or 8 hours, right? And you really have, and then you have to spend an hour to break your stuff down before you can even think about going to bed, right?
Right.
That's when it gets difficult. You see, it's like lost opportunity, but it's not really, because you're starting to get tired. You're going to make mistakes. You're going to
run over your telescope.
You're going to do something, to screw yourself up. And that's
one more thing.
That's right. So you got to really be disciplined and learn how to stop yourself.
Right.
No matter what your passion. It's all about patience, right? This is a long time. This is a journey, like we said before. It's not about any one night.
My wife reminds me, the universe isn't going anywhere.
Right, exactly.
They're still out there.
So you basically, when you're a beginner like I was, I wanted to be able to do stuff the same night I got my equipment, basically, which is folly. You got to spend at least a week probably. If you know this, most beginners don't know any of this, right? That's why I wrote this book. So people, if they have the patience to read the book, then they'll understand at least some things to think about. But again, that's not the way it is. Yeah. And so you just have to coach and mentor beginners in their astrophotography and tell them what's important. And beginners, I've talked to a lot of customers of our equipment. They have certain ideas in their head on what's important and what's not. And it's kind of backwards sometimes. They've read the stuff on forums and other things, and they get a wide gamut of opinions about certain things, and at least half of it's wrong. Probably more, but I'm being generous probably. But so that's the last tip I would have. Just learn patience, and it'll teach you patience regardless. The reality will smack you in the head and teach you patience, even if you don't want to have patience. And discipline in your in the way you use your equipment is a big thing.
Yeah,
that's about all I have.
All right.
Jerry, if I may,
Sure.
I'd like to add one thing about weather, since
Mm-hmm.
that's critical, obviously, to imagers and observers alike. Can I just share the screen for
Sure.
just a moment?
Sure.
There is a site called SpotWX. It's just spotwx.com.
Mm-hmm.
And you just type in, I'll show you the information it provides. Let's type in Santa Fe, New Mexico. And then down here, there are a series of menu items: 18-hour, 21-hour, 3.5 day, and 10 day are the ones I use. Now, the 18-hour will give you temperature and relative humidity, and also the dew point. So you can calculate here, for example, okay, I've got a 5.5 degree centigrade difference between dew point and temperature, which means you're not going to have dew problems.
Right.
Down here, it shows high, mid, and low level clouds. So
Nice.
you can see here it's going to be clear from 12 to 2, and then you're going to have mid-level clouds coming in here. And you can use it for advanced planning, like the 10-day forecast here will give you some idea whether you have a clear night coming up on May 4th, for example. Now that changes, obviously, but it's a great site. I travel 72 miles to my dark sky site. I've done that 73 times in the last 2 years, and I've only been clouded out twice out of 73.
Wow.
I rely on Clear Skies and WX. If they agree it's going to be clear, I can leave in a driving rainstorm here and it'll be clear.
Yeah.
So just another suggestion.
Excellent.
I wrote that down.
that's all.
Yep, I shared that with the audience here too.
I got a screen capture.
Chris Larson says, I feel like I'm trying to drink from a fire hose sometimes, but the joy of discovery far outweighs getting wet all the time.
That's when you find out. That's when you have an interesting time when it starts raining on your equipment and you're trying to break it down faster, twice as fast as you normally would. That's always fun.
Tony Day lives in United Arab Emirates, and he's from the UK, and his telescope's in the UK, and he can't get it, and because of the pandemic situation. But I advised him in the next few months that it's probably going to be possible for him to have his scope again. He came back with mentioning, he said, in the meantime, I love watching the Explorer Alliance star parties from the UAE and avidly keep an eye open for the party days. That's great, Tony. Thank you. Very nice. That's testimony to all of you that are presenters on the Global Star Party and the people who have been the guest hosts of the Global Star Party. It is I think it's wonderful, and that we have such variety and so much knowledge coming from this group. Coming up next is Adrian Bradley. Adrian's been popping in and out here. He was trying to have a live Moonrise event for us, but
It didn't happen.
It didn't happen,
Yeah.
but he's the patient.
Yeah, it got clouded out.
Yeah.
And I know the sites are out there. I actually had a moment where the sky was clearing. I looked at some of the services and saw there was going to be a brief moment during Moonrise where there'd be a clearing. So I took the chance, and although I haven't taken the images out of the camera yet, never did see but a small sliver of the moon moving between clouds. But so one thing that Nightscape photographers will do, so I'm sitting in the car right now doing the presentation, I'm heading back. Chuck, you say you'll drive 73 miles to your dark sky site. I'll drive 156.
Wow.
And I've enjoyed I'm probably going to be driving 73 miles after I do this presentation, listening to the rest of the presentations. It's something, doing nightscape photography is something that's grabbed a hold of me. It's become a niche that I've enjoyed, going out to sites with just a camera, a tracking mount, a sturdy tripod, a couple of lenses, all fast lenses f2.8, aiming for a particular part of the sky, doing some long exposures, some tracked exposures, and seeing what I get. But tonight's presentation was on moonrises because I'd hoped I'd get another one. So I am going to share, let's see, I should probably not share my screen, but I guess I'll do it. Let's see what happens here. All right. So it's trying to share everything on my screen.
Mm-hmm. Hopefully you're not still driving.
Nope, I pulled over because I said I'm not going to try that. So can everybody see the
Yes.
this moonrise photo?
Nice.
Yeah, it's nice.
So
Oh, the windmills, yeah.
Yep, with the
Where are you?
turbines, windmills. So this is back in Michigan. So this is it's a place called Lake Erie Metro Park in Michigan. A lot of what I've tried to shoot, and by shoot I mean taking photos, has been around Michigan where I can drive for sometimes 2 hours, 3 hours, 5 hours if I want to go to the Upper Peninsula and take photos. These particular photos were taken, this is moonrise over a channel that joins the Detroit River and Lake Erie, and it's a metro park. So I had a couple of these, caught some birds flying across the moon.
Okay.
Yep. I also do wildlife photography for fun when if I'm not doing nightscape photography. There's a group of ducks flying across. So this is this picture of this orb coming out of something blue was a poorly processed orangish moonrise coming just out of the lake. So obviously part of the reason I want to do moonrises is because it needs a little more work. I tried it again. It's this was taken with a larger lens, and
But it must have been visually stunning.
Yeah, if you see the moonrise for yourself with your own eyes, it will be stunning. I've seen both a sunrise and a moonrise come out of the particular part of Lake Huron. This is a little bit better, I think, but it purposely blew the moon out just because I wanted to capture the scenery around it.
Yeah. But
So the moon had risen.
The light pillar coming from it.
Yeah, I'll explain that light pillar. It's not the real light pillar. It's a grain of dust that I didn't know was on my lens. I took a couple other lenses. Yeah, if you have a small grain of dust and you haven't cleaned your lens and you take these pictures, you basically produce a light pillar type of effect. And since I had taken real light pillars, I had to make sure that it was real. Because I think it was cold that night. And so, I was thinking, well, maybe it's a real light pillar. And then I used a different lens, didn't see it, and said, okay, it wasn't. So, yeah, it looks like a light pillar, but it's the effect of having a grain of dust on your lens. It makes for a cool looking image. It isn't necessarily, although the moon really is this size, it was really that size when you saw it naked eye. And so this is a composite picture in an attempt to make a beautiful image. Sometimes we make images, other times we try and be accurate with what we see. This is another example of just using moonlight, as the moon's risen pretty well by now. It's up, and using moonlight to illuminate your surroundings and produce this sort of effect with your images where you've got the lighting, the shadows. It's a long exposure, so the clouds stretch out, and you can still see stars. When you're in a dark sky area, you'll see stars even when the full moon is out. And with your phone, and you take a picture as it rises, and if there's crystals in the sky, you see the halo going around it. And this is a very recent picture blue hour. Behind you, the sun is setting. It's below the horizon, and blue hour starts. The moon has risen, and there's a tuft of clouds around it. You can produce pretty neat effects. This one with the sort of the moon burst, depending on the settings you use. The highest number, narrowest aperture on your DSLR camera will produce this. I also shot this low to the ground so that the water, the angle would have a certain look to it. But this is a fairly recent image. This is a fairly recent image of just using the moonlight. The moon doesn't appear here, it's higher up. But this image, I believe, was shot at an aperture of f8. For those that are out there that do photography, you may recognize that aperture is something you'd use during daylight. With the moon out, you can shoot. You have to use longer exposures because it's darker, but you can use all of your other settings can be daylight settings. I've even shot with an ISO of 100, which when it's dark like that, you normally don't shoot at 100, but you can, depending on how long your exposure is. So there's a number of creative things you can do. Yeah, this is my favorite place to go whenever there are no clouds and it's moonless. It is nice and dark. It's about a Bortle 3 sky. So yeah, and this is a lens I picked up recently that I shot this with. I had it out tonight, and unfortunately there was no moon to test it with. This is my surprise shot. I took a lens. I shot at the moon as it was appearing. This was some months ago, I think. The moon was appearing out of the clouds, and I managed this shot using the narrowest aperture that I could, f32, a 5-second exposure, ISO 116 at an 80 millimeters, a lens that was capable of f2.8, had it all the way up. Fired this as I was leaving because I was mad I couldn't get the moon lower to the horizon, and I ended up with this oil painting looking shot with detail in the moon. So I've saved those settings. I was hoping to try them again tonight. The clouds were too thick, the moon wouldn't show. But I thought that was interesting that I could get this sort of detail on the moon. And if I blow this in, it's gonna fade. But yeah, I think Jim Hubbell was saying, once you've learned your equipment to a point where you can start experimenting and trying different things, you're not afraid to try it. I'm asked all the time about settings, and I'm always happy to provide those settings. They're kind of a starting point for, what it is. I'm visualizing what those settings are and using those to try and capture what I'm seeing in front of me. And I think this was the last photo. I'm glad it was, because that was the one I wanted to be the last photo. So now I have to figure out how to stop sharing. There we go. And
that's awesome.
Let's see. Yep, that was. So I have done some moonrises. It looks like my light went out, so it's just you're not going to see a light here. We'll do this.
There we go.
Yeah, this is my light on location. Part of the joy is just chasing. Chasing is the joy. I'm living in a condo. I have a wife who says if you're going to go out there, just come home safe. Right. Driving here and there. And sometimes the chase is just as much fun as acquiring the image. Sometimes you acquire an image that surprises you. Sometimes you change your camera angle so you're not looking down at everyone. So it's if that's the passion, and a lot of photographers, just not even just astrophotography or Nightscape, the passion is you look at what you've got in front of you, you compose the shot in your mind. before you begin to set the shot up. Because unlike just going after a particular object, slewing to the object and seeing if you've got it, you're looking at an entire landscape or nightscape ahead of you. And if you know what the night sky is doing, you can say, okay, I know the dipper's here. I know that this is rising. I want that in the shot. A lot of shots I'll take of the night sky, if Orion is somewhere near there, I'll try and line it up so that Orion's in the picture. So there's that's part of the fun, and it's this is.
Oh, that's cool. That's
I'll
great.
probably be doing some. Yeah,
Adrian,
so
you're
that's
like
my
our
presentation.
Tornado chaser or something. It's from the field. It's awesome.
That's
I
how
love
it feels. But that, yeah, it's a passion. It's a passion of mine to see what I can get.
Yep,
So,
that comes across.
well, there you have it.
Adrian, have you?
Yep.
You look like you might be in a region in the Northern Peninsula where you could get some auroral shots. Have you tried any of those yet?
I have. I would love to. Let's go to photos because I think I have one I can share. I'm gonna find it and then we'll move on to. Let's see. I'll share a couple of pictures. I'll share that one and Zodiacal light. I've taken a picture of that. It surprised me that I actually had one of those. And
could you see it? Could you see it yourself?
With that photo. Yes, I could. All right. So that is a processed Milky Way that I took on the Upper Peninsula, a Bortle 2 sky. And there's the aurora from that same site. I happened to be there the spring solstice in the thumb of Michigan, looking north, and noticed there was something going on out there. And I aimed the camera at it and fired. After a couple of shots to get the stars all lined up, I went in and I started. I had never shot aurora. I had actually never shot aurora before that night. So I used settings that I said, okay, well, I know what I used just to get stars into view. Let's try these settings. And within a couple of shots, I had a picture like this. So it does pay to know your equipment, and I have old equipment too. This is a Canon 6D, about a 12-year-old camera, but it's a full frame, and it's one that Canon staff have said the 6D just was really good at low light shots. And then the lens I used was it was a wide angle f2.8 lens. So I think it may have been an old 17 millimeter. I have a 14 millimeter now, but yeah, when the skies open up north, it makes it worth it to drive out that far. So it's a great thing.
Yeah, thank you.
You're welcome. It's a little different from your classic astrophotography. There's uses for both, and there's use for a dome light. That's what I need right now. There's the dome light. Yeah, I'm gonna be listening as I hit the road and listening to the rest of the presentations and enjoying the banter because I'll probably still be on the road when the after party starts. But once again, Scott, thank you for having me on, and we make do with what we have.
Come back.
And I have a light pollution, an idea for light pollution that I may do at another feature presentation. I've taken a Milky Way in a light polluted area, and then that shot you saw at a dark sky, and the differences are pretty amazing. It's like, wow. So,
right.
All righty.
All right.
Thank you
safe,
all.
Man. Be safe.
Drive safely.
Bye-bye. So up next here is we have Chuck Allen. Chuck has given us several really stunning and amazing, mind-bending kind of talks about the universe and of all of its proportions and you know, he likes to make you think, and I think that Chuck's one of the really gifted presenters out there today in the amateur astronomy world. So, Chuck, why don't you go ahead and take it from here?
Okay, thank you. All right, let's share screen for starters. This is actually going to be kind of a, let's see if I can get rid of this. Hang on just one second, folks. Need to get rid of one thing here. Okay, there we go. Well,
You have your PowerPoint up.
yeah, yeah.
Mm-hmm.
I had a chat box that was,
Hiding it.
yeah. Now I'm having trouble getting back to full screen. Ah. Okay.
The computer hasn't frozen because we can hear you very well.
Okay, there we go. All right, now let's try that again. Sorry about that interruption.
No problem.
This is a series of very easy listening short stories in astronomy. And a lot of it has to do with precovery, that is, discoveries that were missed by people who had an opportunity to do it.
Oh.
And so what we're going to do is just take these at random. There's no particular order to it. The first is the star that moved. And this has to do with the checkered history of the discovery of Neptune. Whoops. Neptune's history was checkered because of a competition that occurred. There were two astronomers who began working on solving the problem of why the orbit of Uranus seemed to be perturbed. And it was determined that it was being perturbed by a massive planet that lay beyond Uranus, planet 8. And so the search was on in both England and in France. The two individuals who were working on this were, first of all, in France, in Paris, Urbain Le Verrier, and in England, John Couch Adams. Now, Adams was the first to come up with a rough idea of where Neptune was located. And he communicated those calculations to James Challis at the Cambridge Observatory in September of 1845, but they were rough estimates. And he didn't want to publish them because he knew that they weren't refined enough. But Le Verrier had calculated the location of Neptune to within approximately 1 degree, and he published that result, Le Verrier here in Paris, he published that result in June of 1846, the next year. Well, John Couch Adams' boss, the Astronomer Royal of England, George Airy, recognized that Adams was doing similar work to that which he saw published by Le Verrier in Paris. And so he initiated a secret attempt to locate Planet 8 to support John Adams' efforts. And he asked Challis to use an 11.25-inch telescope to try to find this Planet 8 before the French did. Well, Challis did find it. He found it on August the 8th and August 12th, but he had bad star charts and he didn't recognize that he had a planet in the field of view. Unaware of Challis's work and using John Adams' data, Le Verrier sent his results to Johann Gottfried Galle at the New Berlin Observatory. The New Berlin Observatory housed a 9-inch refractor, which I will show you here. And Dr. Galle took Le Verrier's estimates of the location of Neptune, and in less than 60 minutes found Neptune on September 24th, 1846. Airy, back in England, rushed to claim credit for Adams because Adams had also roughly produced the location, but not as accurately. This made the French very angry, but Le Verrier was very sanguine about it. He understood that both perhaps should get credit, and this kind of irritated perhaps the French. There was a cartoon, a funny cartoon that showed a view from England looking across the English Channel. And on the French side, Leverrier had his telescope aimed up at the sky at Neptune and was writing in a book. And on the English side, John Couch Adams had a telescope aimed at Leverrier's book, and he was writing in his own book. So that's how testy things got. But Adams gave credit where it was due. He said there's no doubt that the researches done by Leverrier were the first to be published, and that it directly led to the discovery by Dr. Gally in Berlin. However, there was another person, we can skip that, who may have found Neptune first. In fact, he did. On January 6, 1613, Galileo was, of course, observing Jupiter and its 4 Galilean moons, as we refer to them today. And on January 28, 1613, he did another chart noting the position of the moons of Jupiter, but he noticed that there were 2 stars in the field of view that were further apart on this night than they had appeared to be on January 6th. He made a notation that one of these stars had moved. And if you look down here using Starry Night software, you will see that on the night that he was charting the locations of those moons, it was in fact Neptune that was close to that star over here. He had found Neptune and had even noted that it moved, but he didn't make the connection significantly enough to report the discovery of a planet. Then there's the question of who dropped the ball. If I asked you the question, who was it who dropped 2 different weights off a tower to prove that Aristotle was wrong and to prove that objects dropped from a height, regardless of their mass, will drop at the same rate, barring, of course, any interference from air resistance, you would say that it was this person, Galileo, and you would tell me all about the story about how he dropped 2 different cannonballs of different masses off the Leaning Tower of Pisa. This seems to have occurred sometime between 1589 and 1592 and was reported in a biography written about Galileo and published in 1717 by Vincenzo Viviani. Historians believe that it may be apocryphal, that it may have just been a thought experiment, consistent with his work using inclined planes to determine how objects accelerated in a gravitational field. But if you were telling me that Galileo was the first to do this experiment, you would be wrong. Because about at least 3 years before the earliest time that Galileo was reported to have done this experiment, this gentleman, Simon Steven, a Flemish engineer and mathematician, dropped 2 lead balls of different weights off the Nieuwerkerk in Delft, Holland. He was aided by Jan Cornets de Groot, a lawyer in the area. They relied on the audio, the noise of the 2 objects hitting boards upon which they dropped them, and on witnesses who said they indeed landed at the same time. And he published this result in 1586, the same year he did the experiment, basically noting that Aristotle was wrong. So why no credit to Mr. Steven, and why does Galileo get all the credit? Well, but Galileo is the one who used an inclined plane to slow down the accelerating process, and was the one who determined the S equals T squared relationship. That is, that if an object falls 1 foot in 1 second, in the second it will fall 4 feet, and so forth. David Scott, the astronaut aboard Apollo 15, actually did an experiment where he was dropping a feather. Obviously, dropping a feather off a tower won't work because of air resistance on the Earth. But if you can do it in an airless atmosphere, such as on the surface of the moon, you get a very different result. And here,
Yeah, I love this. It's awesome.
Me too. It's awesome.
Yeah. It's so weird to see.
Right.
Yeah, it was
Look
so
at it, he's
cool.
so
What a
happy.
great experiment. Yeah.
Have you ever seen this movie about the robot ball that has a high-speed camera inside? That there is some dust inside. How they're floating around in a weightlessness.
Yes.
You have, Chuck.
Yes.
That's amazing.
Yes. Okay. Well, who's first? These are the first 10 asteroids to have been discovered in order from left to right according to their size. Ceres, of course, was discovered in 1801 by Piazzi. Pallas was the second to be discovered the following year, then Juno, then Vesta. Vesta is the second largest asteroid known, and Pallas is third. This is a close-up of Pallas. And there's a story here, and that is this. Pallas was actually discovered by a person you may have heard of, Wilhelm Olbers, the German astronomer. He's, of course, the author of the great Olbers paradox, in which he said that if the universe is infinite, then all lines of sight would intersect with the surface of a star, and as a result, the sky should be infinitely bright, like this. Of course, the paradox failed to consider the redshift of light coming through an expanding universe, which would make it redder and redder and maybe even invisible at some point, and also the fact that stars at great distances, light has not had time to reach us. So he failed to consider those things. Nonetheless, he discovered Pallas in 1802. But in 1779, before Piazzi discovered Ceres, Charles Messier was tracking Comet Bode, and he noticed a 7th magnitude star. I marked it in red here. This reference to a nebula is constant along this line. He's referring to the comet there, but he noted a 7th magnitude star at this location on the chart. Turns out, however, there is no 7th magnitude star at that location. It was actually Pallas, and had he been following its movement, he would have discovered Pallas before Ceres, and Pallas would have been known as 1 Pallas instead of 2, or 3 rather. Okay, now you see it, and now you don't. This is what amateurs can do. January 23rd, 2004, a fellow by the name of Julian J. McNeil, he goes by J, 32 years old, was using a 3-inch refractor and a CCD camera in his backyard in Paducah, Kentucky, my state. He was taking a picture of M78, which normally appears as a circular smudge with 2 stars in it, as you know, and noticed a fan-shaped nebula next to it in his image. And he reported this, and within 48 hours, professional observatories confirmed his observation of a hitherto uncharted nebula, now known as McNeil's Nebula.
Wow.
It was also found in an image in 1966, and so astronomers thought, well, that period of time would suggest that it might brighten again in 2042. But it brightened again in 2008, and it stayed fairly bright and detectable until 2018 in November, when it disappeared again. Today, there is no hint of it whatsoever. So this gentleman got a nebula named after him, and it's still being watched, and it shows you what can be done with a 3-inch telescope.
Chuck, is that nebula similar to Hubble's variable nebula?
Yes, it is. It is. It's a protostar that flares and illuminates the nebula around it. At what period, perhaps an irregular period it seems, means that it should be watched on a constant basis. There doesn't appear to be any regularity to it based on how long it stayed bright from 2008 to 2018 and then disappeared again. Regarding that alarm, now this is a complicated story that involves the Apollo 11 landing. Buzz Aldrin was the one communicating with the Earth through Charles Duke, the capsule commander. Gene Kranz was the flight director. And as you know, at NASA, the flight director is in charge of every subgroup in charge of specific functions for the mission, one of which is called GIDO, or Guidance Operations. Any one of these individuals can declare an abort if it's necessary. The doctor can, computer operations can. Any system that seems to be failing can call an abort to a mission, and Krantz would have to obey that. Stephen Bales was only 26 years old and was in charge of guidance operations only because his boss was incredibly sick. You'd have to be pretty sick to not be on the job for the landing, the first landing on the moon. And so this young 26-year-old found himself in charge of this operation. Here he is a little bit later in his life. His name is Stephen Bales, and he had working for him a 24-year-old computer operations fellow by the name of Jack Garman. Now, some of you may recall from seeing videos that when the Eagle was at 25,000 feet and coming in its braking phase, there were a series of 1202 alarms that came up on the computer aboard Apollo 11 that Buzz Aldrin reported to the ground. Now, Bales described the receipt of these alarms as a situation in which he stood up with his hair on end, because now this 26-year-old, who's normally not in charge of guidance operations, has to make a call on whether to abort the first moon landing or not. Garman, his underling, told him that it was executive overflow and that it would clear up. If it doesn't occur again, we're okay. It turns out that Jack Garman was wrong. This was actually a reset of the computer. It was not an overflow. And nonetheless, based on that advice, Stephen Bales said, we're go on that alarm. And that was communicated up to Buzz Aldrin. But there were two more 1202 alarms that kept occurring. And then when the LEM got within 3,000 feet of the surface, Aldrin started reporting 1201 alarms. Bales again was panicked. Now they're under 3,000 feet above the surface. They're low on fuel. And Garmin had to rely again on Garmin and give the statement that it's the same type of error and we're go on that alarm. Well, it turned out it wasn't the same type of error. This time it was an executive overflow, too much information being processed by the computer. So the reason they gave the go command in both cases is because they had misinterpreted the nature of the alarm, but they were similar in nature.
Wow.
Bales was actually chosen to receive a special group achievement award on the same night that the three astronauts received Presidential Medals of Freedom. And Bales was chosen to receive this award because of basically his courage in making these decisions to go ahead. Now, what actually happened? Here's the computer face, and this is what Buzz Aldrin had in front of him during the landing. Now, when the LEM was in the braking phase, the guidance algorithms for the LEM took up about 80% of the memory of the computer, and the rendezvous radar, which controlled the thrusters, the various thrusters on the vehicle, took up another 15%, and that was all fine. And then Buzz Aldrin entered verb 16, noun 68 that you see right here. What that is simply requesting some data that appears here. What is our angle of descent? How far are we above the surface? What is the distance to the landing point? He just wanted some information. Well, then the 1202 alarms started. And again, there were three 1202 alarms. And it was only after the second one, Buzz did it again, entered again the verb 16, noun 68, and the 1202 came up again. And finally, very meekly, he said to Neil Armstrong, it seems to happen when we have a 1668 come up. So at that point, Buzz figured out it was time to stop entering this request for information into the computer. And once he did, the 1202 stopped. What was happening was the verb 16, noun 68 request was adding 10% load on the memory of the computer. You can do the math here. It's over 100%. That caused the computer to keep trying to reset to give this information over here without this information. And so once he stopped that, everything was fine until the LEM got down below 3,000 feet, at which point the guidance algorithm demand on the computer started to rise, put them over 100% again without any interference from Buzz Aldrin. And when that happened, the computer started giving 1201 overflow alarms. But you may recall that Neil Armstrong then took over manual control of the LEM because of boulders beneath and a crater beneath the LEM. And when he did that, the demand on the computer for the guidance algorithms dropped to about 40%, and they had no more alarms whatsoever. Very quickly, finishing up here, some new information has come to light about the zodiacal light and what it might be. The zodiacal light is thought to be light reflecting off of dust grains in the inner solar system, and is thought to come from material emitted from comet tails and from asteroid collisions in the inner solar system. It's best seen at sunset in the spring or in sunrise in the fall, when the ecliptic rises at a steep angle to the horizon. Turns out the Juno mission to Jupiter made a rather circuitous route to Jupiter, and indeed, when it was first launched, first flew out into the inner asteroid belt and then looped around for a flyby of Earth to give it faster trajectory to Jupiter. While it was out here, it had a function. It had 4 star tracking cams whose job was to look for new asteroids. It would take 4 pictures a second, but would only send back images if it found something. They weren't expecting too many images to come back. Instead, thousands of images were coming back. Turned out the images that were coming back were particles that were being knocked loose from the solar panels by dust impacts hitting the vehicle at 10,000 miles per hour. They then were able to determine that the orbital properties of the dust matched those of Mars, seen here in the red orbit. As a result, the likely source of the zodiacal light is now thought to be nothing other than Martian dust storms, which somehow have emitted dust incapable of leaving gravitational attraction of Mars and entering the region through which the Juno mission flew.
Very interesting.
Then there's 34 Tauri. Most of you know this story. William Herschel, of course, discovered Uranus on March 13th, 1781 with a 6.2-inch reflector in his backyard. He raised that reflector to 932 power and noticed that unlike stars, the image kept getting fuzzier and fuzzier, leading him to believe that he had discovered a comet. It was actually his friends, other astronomers, who kept observing it and noted that the orbit appeared to be too circular, the image rather, appeared to be too circular and too bright for an object moving so slowly across the sky. And so they convinced Herschel that he actually had something other than a comet. John Flamsteed, however, you know him. John Flamsteed numbered stars in each constellation from west to east. For example, he would start with 1 Orionis, 2, 3, 4, 5, 6, 7 visible stars in the constellations, and move across. These, of course, are omitting some numbers. Here's 16 Orionis, here's 23. So somewhere down in here are 17, 18, 19, and 20, and so forth. One of the stars he cataloged was 34 Tauri. Well, it turns out that 34 Tauri doesn't exist today. We can't find it. And it turns out that what he actually saw and cataloged as the star 34 Tauri was the planet Uranus itself. That was in 1690. He could have had the discovery some 91 years before Herschel did it. Wow. Also in the late 1750s, Pierre Lemonnier observed Uranus 12 times, and indeed observed it on 4 consecutive nights and wrote it in his log, but never noted that it was a planet or determined its motion. They called him for this sloppy Pierre because of his record keeping. Here's an interesting tidbit. Those 3 Galilean moons, what? There are 4. We all know there are 4. Galileo found them with his little telescope. And we all know that they're huge moons: Io, Europa, Ganymede, Callisto. So why 3? Well, it may be that someone else discovered Ganymede. Xi Zhizong in China postulates that Ganymede was discovered by Gan Di in 365 BC.
Wow.
He found a record that Gan Di had indeed cataloged a small star next to Jupiter through naked eye observation. And this can be done by simply occulting Jupiter and knowing that Ganymede's on the side that won't be occulted at the same time by a tree limb. Wow. So it is possible at magnitude 4.5 that a tree limb blocking Jupiter's light could allow you to make, in this case, a pre-covery of a moon some 2,000 years before it was actually discovered. Since we're running a little late, I'll just terminate it right there, and hope you enjoyed the stories.
Yeah, that was awesome. I'm going to have to try gone to the technique there. So that's very cool. Very cool.
Oh, just
Well,
amazing.
Yes. Well, lots of great comments from the audience too, Chuck. So
Yeah, and remember to check your own data, because I almost discovered a supernova. I was a couple days late, and I didn't think to look at my data, and I went and looked at it after the announcement was made, and I was like, dang, it was there in my data. So blink through your galaxy images once in a while from different times, and you might catch something. Amateurs discover supernovae and variable stars and novas all the time.
yes, that's right. That's right. Well, how's your skies tonight, Molly?
They're good, and I do have a target to show.
Great.
So go ahead and switch screens here. So this target it's already set behind my tree, but I got some frames on it before, and I took a screenshot to put this up. So this is just a couple of minutes on what was formerly known as the Eskimo Nebula, but we're trying to do away with that name. And an alternative name that I found in the Sky Safari app was the Clownface Nebula. So NGC 2392 is a planetary nebula. It's rather small. So if you look at it visually, it's very bright. If you look at it visually, you'll see it as kind of a turquoise. It's big enough that it doesn't quite look like a star. It looks non-stellar, and it's kind of this turquoise color. You can kind of see the disc shape of it. Mm-hmm. Now, this is with an oxygen 3 filter, and had I been able to take more frames, you might have been able to see some of the structure start to arise. Let me pull up a processed picture I have of it. Let's see.
Yeah, even on that shot, Molly, I can see the.
You can kind of see the central.
A couple of the filaments. Yeah.
Yeah, there's kind of a like a central bright ring, and then there's this dimmer halo around it, and that's where a lot of the structure is. Let's see.
Yeah, but even in that dimmer outer ring, like I said, you can see some of the other. Yeah.
Now I've got just a small chunk of my screen showing here, so let me get this in here.
Oh yeah.
So this is a processed image of it with I don't have on hand how much, and it's something like 20 plus hours of data. A lot of this is narrowband. And actually I've got this kind of you're not gonna be able to get it. Let me get this back on screen here. Yeah, so this is a lot of hydrogen and oxygen data. And so you can see that ring, and you can actually see that it's not quite circular. It's kind of oblong. And then
triangular almost, yeah.
Yeah, and then in the outer ring, the hydrogen is kind of splotchily. It's not evenly diffused. It's kind of going out in splotches. So it's interesting because you might think that a star might eject its gas isotropically in all directions, but as we see in a number of planetary nebula, there's a preference for certain directions. And it's not all, I mean, the star is rotating, and that certainly has something to do with it, but even then it's not always symmetrical either. So it's really interesting.
Yeah, when it exhausts the gas, I mean, even like obviously our sun, we have different solar cycles and the distribution of sunspots, etc. You can imagine that happening on with an explosion like this.
That's a good point. These are like really slow explosions. So the star is still going to be changing as it's ejecting that material. Yeah, that's a good point.
Different chemical makeup. Kind of to your other point, that particle physics. Yeah.
Yeah.
Beautiful shot, though.
Yeah.
Wonderful.
That's really nice.
Great. So, Molly, I know that you do a lot of different programs. If someone is a beginner in astrophotography, Where would you, what's your top 3 go-to places to send people to learn more about astrophotography?
Ooh, I have some tutorials on my website.
Okay, well, there's one. And what is that website again?
Astronomaly.com. And I have I have what I call my super duper primer series. That's just like some of the early stuff that, how to connect your camera to your telescope, how to auto guide, how to do planetary imaging, how to process a deep sky stacker. I have a PixInsight tutorial, but it needs to be updated. And I've been working on some new tutorials, but haven't quite gotten them done. I do have one YouTube video.
Okay.
on PixInsight processing, but I actually, from the very beginning, I used one of the books in that Patrick Moore astronomy series called Astrophotography on the Go, and especially if you have an Altaz mount, it's got some useful bits in there on how to do astrophotography on an Altaz mount, which is what I started on, and it's a good reference. I'm not myself a big YouTube watcher, but the Astro Imaging channel has, I'm going to plug another thing of mine, which is the Astro Imaging channel. We have tons and tons of content. We have over 300 videos on everything from beginner topics. Like we have, this weekend, we have a talk by a guy named Ken Daly on how to focus your telescope or your camera. All the way up to, we have Warren Keller and Adam Block on there several times on how to do stuff in PixInsight, really advanced processes and stuff. So really a wide variety of content to cover all expertise levels and stuff like that. And yeah, trial and error. Yeah. I just got that a lot and messed around with stuff. And you'll see a lot on the forums, people will say like, oh, you can't do astrophotography with this, or like you have to do this in order to, like you have to auto guide to do astrophotography, or you can't do astrophotography with a Schmidt-Cassegrain or a DSLR. But while it is harder to do astrophotography without auto guiding or with certain telescopes and cameras, you can get, especially if you're just starting out, you can get some really exciting results without having to have really fancy gear. And in fact, you can just toss a DSLR on a tripod and do some really.
Oh, absolutely. Yeah, so, that's right.
Whatever.
Yeah, I've seen astrophotographs, of course, with no tracking at all, and a lot of us have. I've seen people take completely manual equatorial mounts, like the ones with the flexible cables, and actually track by hand and get pinpoint stars. Wow. That's extraordinarily difficult to do, but I've seen it done.
I've seen some really good planetary and International Space Station images from hand-tracked Dobsonians.
Yeah,
I've personally had more luck hand tracking the ISS, with the hand paddle on my computerized mount.
Oh, okay.
But I've had more success doing that than having the mount try and do it. So, I've seen whatever gear you have, just try stuff. You can never Yeah,
I'd love to share an example of that if okay. It'll be a really quick example. A DSLR, a 100 to 400 millimeter lens on a tracking mount and on a tripod, and I think I have it queued up.
I've gotten some really nice results with a rig like that. Yeah,
pointing it at the sky. Let's see how this works. Okay, it says I'm sharing my screen. That's nice. Now share it. There. Everybody see that?
Nice. Yeah.
Yeah, with that rig. Also fairly dark skies. Now you can pixel peep this and you'll look at it and you'll go, there might be some halos or it's a little fuzzy. Well, there's another view of it. That was cropped in and processed. I actually like this one a little bit better. I think it looks a lot better. But and this was not a modified camera either. This was an unmodified camera, same one I used to do daytime portraits, both filters intact. orbital 3 sky about a 3-minute exposure, or actually less than that. I think this was it may have been a 90-second exposure or something. It was not a long exposure, somewhere around 2 minutes, and end up with that. So a lot of factors do go into it, like you were saying, Molly, and it's
Yeah.
you know, it's something where you can't limit yourself to just thinking there's only one way to do something. There's many ways to do it, and you know, it all depends on where you're willing to drive. That was a 3-hour drive for me to get to a sky like that and be able to get that image. And it was a last second, let me try it thing, because what I wanted to do at first got, I think it got clouded out where I originally was. So, you know, and then that happened. So yeah, just backing up what you were saying, Molly, and you know, everyone else, aim at the sky and see what you can get. And, you know, it's different types of equipment can get the job done.
Yeah, and yeah, whatever you have. This is another example of this is with a like a 50. I think I had the lens like a 55 millimeters f5. I think is just the kit lens, and I took a bunch of 6-second exposures sitting on a tripod, so no tracker, unmodified camera, and it's not, you know, a great shot. Like I've gotten better ones since then using a little DSLR tracker, but this was you know, within my first year or two of astrophotography, and it was really exciting to see the Orion Nebula and the Flame and the Horsehead, and you know, and for a beginner, this is a nice shot and an exciting one to kind of carry you along on the journey. So yeah, whatever gear you have, just try it, and you can figure out how to refine the process with whatever you have, and just experiment, mess around.
Great.
Yeah, it's definitely not
Just mess
yeah,
around.
definitely not about the gear. The gear is a tool to help you if there's certain things you want to be able to do a little bit more. Gear comes into play, and it's kind of the same with regular photography as well as astrophotography. I find, you know, in my experience, I find I may want certain gear to do certain things easier, or, you know, see certain things. Certain gear will help me, but I have noticed there are those that'll swear by certain gear and say it's the only way to do proper astrophotography. And I think we've talked about it all Star Party long, is that we sometimes get it backwards. It's not the gear, it's the person using the gear and their expertise and even knowing what it is in the night sky that you can go after depending on the season. So
Yeah.
if you learn nothing else out there, just try it with what you've got, and don't be intimidated if you go on a forum or a site and you're told, well, you have to have this gear, or the site has to be this dark, or, you know, or you have to build your own observatory to really get good results. You know, just go with what you have. Go figure out the process. We've heard some books that even I'm thinking I need to check out that site and see what else I can learn. I just downloaded PixInsight. I went into it. My brain blew out of the left side of my head, and after I put it all back together, I decided the only way I'm gonna get this right is to go look at a tutorial and then start gradually going through to see if my Nightscape and Milky Way images will benefit from running them through some PixInsight flows. So that's to come. But in the meantime, the moon showed itself up, so I stopped, took a picture of the moon, and then took a picture of lightning because a storm was chasing me.
Nice.
The comment about storm chasing, yeah, well, it was kind of real. I drove out of it, but I do have a picture of a flash. It's not a bolt of lightning, but it's a flash of lightning coming from clouds and then it started to rain on my gear. So it's still been an exciting night, even though it's been a lot of fun. And yes, I'm driving safely. I'm not looking at a screen right now.
Okay. All right.
Looking at the road.
Long answer to a short question.
Don't try this at home.
Okay. All right. So up next we have Cameron Gillis in Seattle. He'll show us some of his most recent work, and then and following Cameron will be DT Gautam from Nepal, and she's going to share her first image that she's ever taken through a telescope and recite a poem that she wrote as well. So I'm looking forward to both of these here. Cameron, you've got the stage. Thank you, Molly.
All right, thanks.
Another amazing night.
Good stuff, Molly. Good stuff. So yeah, let me try this out here. I'm going to share my screen. I have two different sessions, and actually I was on your site there, Molly. And let me just, I found out a way to connect my tablet. So that's, let me just share my screen on the tablet now. Here we go, Smart View. Do that, start that. Okay, can you see my tablet screen?
Mm-hmm, yes.
Okay, great. So, okay, so basically what I'm showing here is Sky Safari. What I've been doing over the last year, talking about the journey and of discovery, ever since, I guess, the pandemic, I had extra time to focus on my astronomy hobby, and so I was kind of rediscovering that. I got really busy with work in the past, and then now with traveling and all that, and now I'm really happy to be able to spend my nights and evenings at home and really dig in. So I got a go-to telescope, and I started to and then I got this this application, Sky Safari, and started to make a sky survey. I wanted to go back. I have Sky Atlas 2000, the paper edition, and that's what I was using before. But I wanted to kind of upgrade and start to do a survey and look at all the different objects down to the magnitude limit of my new Schmidt-Cassegrain, my 8-inch, and kind of rediscover. And in fact, you know, in the past, with I used to have an 18-inch Dobsonian, and I would kind of dive into galaxy clusters and that kind of spotty, and it was really cool. I mean, you could see some beautiful things, but I had a limited sky where I had a darker sky. It was more like Bortle 4. But anyhow, so now I wanted to take a more structured approach, and my ultimate plan here is to categorize all the different objects I can see visually for each constellation, down to, in this case, I went down to 13th magnitude, and then started to identify and categorize and log each one and I've done that over the year, and I'm still not finished, but I've actually done the full set of constellations on all the seasons now, and then I'll show you what I've done. But basically, the next step is I'm going to be buying an imager, probably one of the ASI. I think the 294 is the optimum for my gear, and then basically start imaging each constellation by constellation, all the different objects, so I can kind of use it as a visual enhancement. Because I'm a visual observer from my years, but I really see astrophotography as a way of kind of enhancing that, even going deeper and really exploring and rediscovering. So I want to start categorizing that. So what I've done is for example, let's just take sextants here. Okay, I just go in and go planner, and I'm just going to make it simple. Choose galaxies down to 13th magnitude here. Sorry, I don't know why it's not. Oh, I can type. Okay, good. And then I go in, and I'm just going to choose sextants. There it is. And then do search. And then I'm going to make an observing list. So what it does is it just creates an observing list. And then I go to my observing list, and you can see I have a lot here for every constellation. I did different observing lists at different magnitude thresholds for different objects. And then I have a best and brightest, which is my catalog that I'm working on. And so if I go to search results, and then I go actions, highlight objects, let's just choose them all. And I'm going to go unobserved. And then what I do is I highlight that. And I go back. And now you'll see that in sextants, everything that's down to 13th magnitude galaxies are highlighted now. And what I've done, the important thing to note here is I chose unobserved. Okay, so when you choose unobserved, I actually have in other lists, I actually have observed some of these. So for example, I zoom in, and the Spindle galaxy, for example, it's magnitude 9.1, and I can show my past observation, which I did in April, and my description is bright and beautiful elongated oval with a hint of dust lane and bright oval core. That's what I typed in when I did it, cataloged it before. But what I do is previous to that, I created this observing list. And let's say I observed the Spindle galaxy game. I just go create new observation. I'll say bright, beautiful oval, distinct oval, let's see.
Mm-hmm.
And then I basically go seeing, let's say it was slight quivering. I choose my equipment. And the thing I want to show you is that once I've done that, you'll notice that box disappears. So what I do is I start to go through methodically. And let's just do another quick one here. I'll just make a very simple one. Create here, and they'll say oval patch. Oops. Oval patch. And then I go. You'll see that disappeared. So basically, I start to go through, and then it starts to, each of these objects go away from my list. And at the end of the night, I can just look at my sessions. These are all my sessions, and you can see I have 2 sessions here.
Mm-hmm.
And basically it goes. So what I've done to show you on the grand scale, as I go through this, another thing I want to show you is I found 2 galaxies here. For example, this is 11.9 galaxy, and here's 11.9 galaxy in Hydra. Okay, so it helps me train my observing skills and also set expectations for smaller scopes as well. So if I have a night where, for example, I want to just pull out my 4-inch or 3-inch or different telescopes, I can right away. I don't look for something that I cannot see because of seeing conditions or whatever. I can right away categorize it. So what I've learned, we all know about surface brightness and all that, but I want to show an example here of 2 galaxies, both exactly 11.9, but the description here of this one is distinct oval patch with brighter core. So there's some structure, you can see something, it's very clearly visible, you can even see it with direct vision. But then we have this other one, and again, show observation. Diffuse elongated patch, right? I mean, it's very, with averted vision, I can see, barely to recognize it, but I can see it's elongated. Now, if you look at the actual details, you can see this is 4.2 by 0.7 arc seconds. So it's quite long, or arc minutes, I should say, 4.2. So keep that number in my mind, 4.2 arc minutes. And this other galaxy, oops, sorry, I picked the information. It's 2.3 arc minutes by 1.2. It's a little more oval. It's not elongated, but the over surface area is much more condensed. So now if you go to the DSS image, you can see this is pretty much what I see. I want to actually create my own version of the DSS image. Obviously, the Deep Sky survey has been done, and there's lots of surveys out there, but I want to do my own and basically create a catalog of these types of image, and also to set expectations. What does it look like visually? So this is a long project. It's a lot. It's going to take a long time, but I just wanted to give you a snapshot where we're at. So if we compare it to this one, if I go show observations, sorry, no, wrong one. Information. This one here, DSS image. See, so I described it correctly. I haven't looked at these. This is what so my observation was correct. But obviously the DSS image makes it the surface and then luminosity higher. But you can imagine this spreads out the magnitude. So that 11.9 magnitude is spread over this elongated view. So what I've discovered, even 10th magnitude galaxies, some 9th magnitudes, if they're spread out quite a bit, you have no chance of seeing them with Bortle 6 or Bortle 8 skies. And so anyhow, so now if I look at my grand scheme, I'm just observing this. If I look at what I call best and brightest, and I do all, highlight that, you can see I've seen 688 or 668 objects that I categorize as best and brightest. So these are the objects I've seen over the course of the year.
Wow.
Not only that, I've seen more than that. I've seen actually about 2,000, maybe 3,000 objects. But I've categorized 600 of them as, even in a moonlit night, you can still see them because they're distinct, right? They have a high enough surface brightness to come over the Bortle 6 scale skies. So especially I must say what I was saying last week, but I just want to highlight Virgo is extremely intimidating. Coma Berniceus and Canis Venatici, those are extremely dense galaxy populations. So I just wanted to highlight this tool makes it actually possible so you can keep your sanity as you go through and do your galaxy hunting. And again, if you just look at this group, well, let's just go to something that everyone knows. Here's Mercurian's chain. And you can see most of those galaxies are all in the best. They're all categorized as best and brightest. So that means they'll be visible in a smaller scope, and because they have a high enough surface brightness. But there's a couple, like for example, this one up here, it's 11.9. Now, normally, if that was the right surface brightness, it would actually be able to show. But if I look at the description, diffuse elongated oval patch, right? So, for example, anyhow, that's just I just wanted to give everyone a little tour and kind of snapshot of what I'm up to, and it's not going to be done anytime soon. Again, I'm enjoying the journey, and I just wanted to share that with everyone. So,
well, thank you very much. That's great. I think people are impressed with your, the way that you're recording these objects, and I think any kind of project like that is definitely worthwhile. If you ask David Levy, he'll tell you that you haven't made an observation until you've written it down. So, that's you can look, but observations are recorded. So, yeah, we go from Seattle all the way over to Nepal. It is coming on 11 o'clock in the morning there, and we are, I think we're like 13 hours difference from here in Arkansas. So, DT, thank you very much for coming onto our program and sharing your love of the sky. And so what's happening now?
Yeah, doing great. Hello, everyone, and great to be here. And here I have clicked my first image of the moon, of the
The very
super
first
moon.
image, your first astrophotograph, right?
Yeah. Okay, I'm going to
Wonderful.
share it.
Okay.
Here it is. Yeah.
Oh, wow. Okay.
Yeah. Image.
Okay. So you did this with maybe your smartphone, is that right?
Yeah.
Very cool. Okay.
And
So,
I have a 660x telescope. Yeah.
and you threw a little math in there
And
too.
I have one poem.
Yes.
Yeah.
Well, it's a beautiful image of the moon.
And
So you're going to want to keep that and record the time that you took the image and just keep all that data, you know. Very good.
okay.
Very good.
Yeah. And I have written one poem. The gives the star. So okay. Somewhere in the interstellar, you are always mine. Though you don't love me, I am always there to love you infinite. Gaze, 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 gaze the star. Look those moon and twinkling star. Let's make promise that we will not apart. Come, let's look up the sky and make our togetherness bond. Is black hole and defeat all the warns. Gaze, 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 gaze the star. Let's travel in the starry night and have some cute fires and talks between each others far away in the interstellar night. Gaze, 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 gaze the star. You and me are not apart, similarly formed by stardust. Our interests match as we are same part. Come on, let's look up the sky and share the happiness most. Gaze, 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 gaze the star. Yeah.
Beautiful. That's beautiful, Deepti. You'll have to send that to me. I think it's wonderful. I think it's wonderful.
Yeah, sure.
Yeah, that's great. It's great.
Deepti, I have a greetings from Stockholm, Sweden to you. Can
Yeah.
you hear me?
Okay.
Okay.
Yes.
Save that picture because in 2 years from today, that picture
Yeah.
will mean to you everything because you will compare your journey from that picture.
Yeah.
So keep that safe because if I had today my first astrophotography, I had it in safe with code, you know, fire
Yeah,
safe. So keep that in a safe place.
Yes, that's right. Yeah, these
Of
those
course.
first recordings and first attempts are very special. That's right.
Yeah. It was captured around the 11:48 p.m. At night.
Mm-hmm.
And I have those record, so I will be keeping it safely for the later one.
Yeah, good.
DT, what was your inspiration in writing your poem? What was the inspiration? Is just your feeling for the night sky, or did something special happen?
And now for the, I used to write the poem. And, actually, I like writing the poem story and others
Yes.
Writing the script of the dramas and others. I love those. So I usually write these all, and it was the recent poem I have written. And I usually write usually write the Nepali poem, and so this time I have tried. Why not to try the English one and connect with the astronomy?
I'm impressed. So that's very good. Thank you.
Yeah.
Thank you.
Yes.
Scott.
Yeah. Yes.
Can I share some pictures?
Of course. Go ahead.
Okay, thank you. This is the moon tonight with 300 millimeters and manual focus. It's not good, but it's from tonight. Let's see. Share screen. Nothing happens. Why? You have there. No.
Here we go.
And this is,
That's pretty good.
yeah, it's.
Oh, that's nice. Nice and clean.
Yeah, it's
yeah.
nice.
This is from my headphones.
Beautiful.
Okay,
Yeah,
that's
it's hard to take a picture. Yeah.
And I have some 2 movies that I shot. It's looked like a picture, but it's movie.
Yeah, you remember, Pekka, when we did this the other day, actually last week. I think there's an interesting technique we can do between all of us here. So taking a picture is one thing, that's awesome, but the video, if we can, what I've learned is the video that you take with the phone. Remember when I was sharing the screen with my phone, I was not actually taking a picture. I was not taking a picture. And I was not taking a video. So I was offloading. The processing was all being done on the back end over the Zoom meeting. Think about that. So so here's the interesting thing I think we might discover is that I am just playing with the pro settings on the still shot picture, but you're taking the video on Zoom, right, Scott? I bet you we could probably do something cool where we take really awesome pictures, because I looked at those videos afterwards and it came across actually pretty good. Some of it got a little bit mushy because of the uplink was a little bit compressed, but for the most part, that's way better than I could ever take with my still shot. Or
this is with an 80 millimeters ED telescope and ZVO ASI 178 mm.
Okay. Yeah. But what I'm saying, Pekka, but if you set that up and you don't actually take the picture, right? Set up the settings, the gain, or everything with your ASI with your phone, and then set up a Zoom meeting, and then record.
Yeah,
that.
It's hard. But I love taking movies and spare the movies and then process the movie to one shot. And
anyhow, it's just an idea. Yep.
The last one of Chicard. And you can see how nice the weather was.
Yeah, it's pretty still.
Yes, it's a dream evening when I shot these pictures. So that's all for me.
Great.
Nice.
Great.
I love to shot moon. It's my favorite, and that's how I get into astronomy. It was the moon.
Yes.
And it's hard to leave it.
I love the moon too. There's some astronomers, they don't like it. They say it wipes out all their deep sky objects and everything. I of course love deep sky objects.
Me too. But the moon is
galaxy. The seeing distant galaxies is really what intrigued me to get into astronomy deeper and deeper. But the moon is very, very special to me. You know,
for me, it's almost everything.
Yeah.
But when I was 8 years, I saw that Finland. I thought, why is there Finland in the moon? And I am a Finnish 8-year-old boy. That has the meaning. That has to mean something.
That means something. That's right.
Yes.
That's right.
And I got stuck on the moon.
That's very cool.
What I love best about the moon, observing the moon, and Pekka, I think you captured this the other week, is when you have those thin clouds going by, right? And you can still see the moon, and it really gives you a neat, you still have really good view, and you still have, and you have a little bit of animation as well. So it's really neat to see that. So even if there's clouds, you can check it out.
Yeah, I was just reading today about the air, how the air is going in the atmosphere, and I have begun to use an infrared pass filter, 652 and 752, because when the light comes from moon, it's all colors spread out, and that's why you can't. If you use one shot of one wavelength, you got that wavelength, and you can take a good image when you just capture one wavelength of that spread color from the air movements, and you take just one wavelength.
Well, also, there's just so much to explore. Oh, Scott's bringing out the big guns.
I want to show you guys this. This is, we've talked a little bit about Buzz Aldrin tonight and how they landed on the moon. Buzz Aldrin has one of our telescopes, and he actually sent his telescope back to me to be cleaned and collimated and everything. Now, if you see that plaque right there, that is Buzz
Aldrin.
Buzz Aldrin. But you see how it's black in his face mask?
Yeah.
That is a piece of lunar meteorite in the mask. So we made
No
this
way.
for him. And so it's been a real pleasure. I have a photograph of me standing next to Buzz Aldrin with his telescope and in his apartment, his condo. And but he loves looking at the moon too. And,
Scott, I have a question about the ED127 triplet, and I am on my way to order any day from Finland. And I'd like to ask a honest question. Is that very good for moon photographing?
Well, I think so.
Okay.
I think so. I chose for myself to do astrophotography the 102. Okay. And the reason for it, and I might suggest that you take another look at the 102 because of the focal length. Okay. If you are going to be doing
mostly moon
eclipse work for in particular. I think the 102 is a fantastic scope. It's got more image scale than the 80. The 80 is very, very popular for eclipse work, but the 102 is flatter, more focal length, so more image scale. The 127, during the 2017 eclipse, I did use the 127 visually on the totally eclipsed sun. So it was spectacular to visually look through a telescope with no filter right at the total eclipse, and so it was beautiful. So much detail and everything. I just wanted to keep looking, but I knew, okay, you better not keep looking. Take your look, enjoy it, get that solar filter back on, and when it's time. So,
but eclipses are so rare here in Sweden.
They're rare everywhere, So,
but even more rare here
more rare there.
Yeah. If there's a lunar eclipse, then there is cloudy.
Right. But you could do H alpha work, hydrogen alpha, and there are nice filters that you could put on a 102. And
so 102 is more.
Yeah, I really enjoy it for that. If you are going to do careful studies of craters, mountain ranges and stuff, you do need more focal length, and I think you would enjoy the added aperture of the 127. If you don't have very good seeing conditions, you can always make a mask to stop it down. Okay.
A little smaller.
But you can't, of course, make a smaller one bigger. So, right? So that's the deal.
Okay, I have to look that because he can. I think he has none in store in warehouse.
Yeah, that's the problem all over the world.
In July.
Yeah. So we are expecting more inventory to come this summer. So
I have to ask Scott, what about the 114? The 114 to me, like the FPL 53, looks like the dream machine to me. That is a real special scope.
We have more plans for that focal length and that aperture. Probably would see it come out next year. We did introduce FPL 53 telescopes. They sold slowly because they were so expensive, you know. So,
Yeah.
but there's you know, a lot of enthusiasm for the focal length, and so while I haven't made a final decision yet, I think I'm going to go with FCD 100 glass. It's a lot less money, and it's so close to the same performance.
It's my
Well, you know what?
astrophotography.
Very nice.
Oh, wow.
Beautiful.
Nice.
Yeah.
Oh, wow, you got the motofocuser and everything.
Yes.
Man,
Yep.
that's what is the what's the imagery you have on the main scope? What is which one is that?
This is
Not
an
the
ED80.
guide. No, the imager. ASI, was it the
178.
178? Oh, okay.
Yes, and
Yeah.
120.
And look at the guide scope up there too. That's really,
Yeah.
I've seen that guide scope. It's very nice.
It's
Very,
a
very nice.
50 ED.
Yeah, right. An ED.
ED 50, yes.
But you know what, Scott? The reason why I asked about the
shoot with it.
114.
I can take a photography with it.
Yes, you can.
Yes.
I'm just imagining Scott with the 114 with your 3-inch diagonal, you know,
Yeah.
with the 120 9mm. Oh my gosh.
Oh yeah,
that
yeah,
must be
yeah. Right.
at that focal length, it would be astounding.
That's true.
You go with a dark sky with that guy. Oh my gosh. I mean, it'll be amazing.
Sure.
Anyhow, it's my dream.
Yeah.
Sorry.
Well, no, that's very cool. Well, I think that it's now what time?
It's
20
past
minutes
midnight for
after
you.
midnight here in Springdale, and we've got a big day tomorrow. But
This is the big boss.
oh, that's the big.
120 ED.
Pekka's just getting started.
Yeah, that's
Scott,
right.
watch out.
Right. How many telescopes do you have, Pekka? How many?
I have, I think,
More
8.
than I thought.
8
I thought he was a lot.
telescopes. Wow.
Yes.
Yeah.
CSTs, 11 inch.
What? 8 and
11 inch and 8 inch
Yeah.
CST, and
Wow.
120, 80, ED 72. And I have Orion short tub 80, the old one, not
Yes.
the new one, the old one. That's better.
Oh, okay. Mhm.
And I have small ones, and I have an Astromaster 127 Newtonian.
Oh, okay.
I never used.
No?
No, I got it so cheaply.
Oh,
The story is that I was after the Celestron's, the phone holder,
yeah.
Chooks something.
Next YZ. Yeah, next YZ.
Yes, and that was a package. And I told him
You
that
wanted that.
I wanted that, and he said, no, you have to buy the whole
You
package.
got to buy the whole thing, and so you
Yes.
just bought it all. And
No,
then,
I didn't buy it all. Just to
Yeah.
get the phone, because there was none stuck here in Sweden
oh
for
yeah,
that. So I had to get that one.
yeah.
So I have to buy all the mount and everything.
Everything,
Yes,
everything.
just
Had
the
to.
phone holder.
Yeah.
That's astronomy.
Yes, it is astronomy. That's right. Well, I think we're going to be calling it a close for tonight. It was a great start party. It really was. Cameron, you hung in there for the duration. Thanks for being there and commenting and sharing. And so
My pleasure.
I think the next Global Start Party will be, Cesar Brolo will be the special guest host.
All right.
So I'm looking forward to that. That'll be really interesting. And then we have, I know that Libby is interested in being putting together one of the global star parties, which will be interesting. And so is Deepti. Deepti is also looking to be a special guest host as well. So I look forward to all the people that she could invite and get involved here with Global Star Party. So
I say, Scott, that this is the one of the best one. of the
Oh, you like this?
Astrophotography.
Yeah.
Yes, it has been so interesting show.
Yeah, it's really interesting talks. And you know,
Yes.
Well, this one seemed to
feel
talk a
charged
lot
up a
about the
little bit.
moon.
That's
You know
what
what?
we're after.
You know what, Pekka? The last one is always the best one, and
Yes,
it's getting
but
better all the time.
yes, because
Right.
you get used to it, the camera and the
Yeah.
speakers.
Well, we're
a little
all
bit
friends here now.
slowly.
Yeah.
A little bit
Yeah.
slowly. I have to take a little bit slowly because you are so excited. You
Yes.
are like sprattling of enjoy.
Enjoy the journey. It's fun. It's really
Yeah.
fun.
It's really
Yeah.
fun to share the joy.
And I want to thank all the audience that's watching now and had
Yeah.
watched tonight. We always have people that watch it more in rerun, but right now we have had a reach. Let me look. And this is just Facebook numbers. We're simulcasting on Twitch and Twitter and YouTube, but a lot goes on here on Facebook. We reached over 2,170 people. We had 545 engagements, and let's see how many shares we got. We got almost 60 shares. We're at 59 shares. So that's a lot of different groups, a lot of different people. We hope you enjoyed it. We'll be back next Tuesday with Global Star Party 44. So thanks a lot, and you guys take care, and good night.
And good morning.
And good morning. That's right. It's already morning.
It's
Good morning,
7:30.
everybody.
It's 7:30 here.
I'll be at
Good
home
afternoon.
in about
Yeah, and I think Deeply
35
might
minutes.
already had her breakfast. She's looking for lunch right now. So, and I'm looking for the bed. So,
Yeah.
Yes.
good night. Thanks,
you,
Good
Cameron.
night,
Scott.
Scott.
Take care.
Awesome
all right.
stuff.
Good night,
care.
Take care.
everybody.
Thanks.
Bye bye.
Bye.
Bye
Bye bye. Good night.
bye. Bye bye, Deepti.
Bye, Titi.
Bye bye.
It's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.
Good night, Cameron. Take care.
Good night. Good night, Scott. Thanks.